I'm exhausted. I'm planning on sleeping this entire weekend after this is over. Once again, the warning, this is not the world's safest field to be in for lots of reasons. It's a controversy. And as I mentioned, we've been through a lot. Last time, we talked a little bit about helium-4 as a product and amounts commensurate with energy, time correlated with excess power, and the Q value, meaning energy divided by number of helium-4, being near 24 and being 2 is the only two experiments that have done where the helium is, an attempt is made to scrub the helium out of the cathode. Question of how much energy the helium-4, the alpha particle, has when born is of interest. You can't put a nuclear detector there without interfering with the experiment. The brainstorm was to use the palladium deuteride itself as a nuclear detector. We calibrated it, we went back to experiment, and saw that there's no correlation between neutrons and energy produced, and the background neutrons that show up in experiments are present at a level at or below 1 neutron per 100 joules. We can use that with our calibration palladium deuteride detector to establish an upper limit on the helium-4 energy, the alpha particle energy, near 10 kilovolts. And that rules out all plausible Rutherford-style reactions as candidate explanations, which means we're looking at something fundamentally new. We sort of understood that going into it, but this is a confirmation of it. Question is the energy is not going into energetic nuclear products. Where does the energy go? We've got exactly one experiment that sheds light on it. We've got the 2 laser experiment, so triggering excess heat with 2 lasers, where the system responds at the beat frequency is interesting. However, the fact that it stays on, we have the interpretation that it's staying on because energy is being drawn to the vibrational mode from the nuclear system. We also looked at the issue of current density and flux as a way to trigger. The key theory issue, I guess we began talking about theory last time, is the absence of commensurate energetic nuclear products, which in nuclear physics literature and textbooks, you're not going to have energy production without energetic nuclear products, but in these experiments we appear to do it. And we went through an overview of the theoretical approach. Last time, a very rushed and high-level summary. Today we're going to spend a little bit more time on theory and try to begin connecting theory back to experiment. Our first task is to think about the fractionation problem in terms of models. And in a sense, this is part class and part a little bit of a discussion of some recent results, which I thought might be interesting. Place where things start positive to level systems and oscillators. So we discussed last time that there were models that had been developed that are capable of describing coherent energy exchange between systems with mismatched or incommensurate quanta. So the idea is that if you have a 2-level system, very high energy, oscillator, low energy, normal intuition is it's hard to have the two talk to one another. However, it's well known that it's possible for coherent energy to exchange within established models, and the effects have been observed experimentally. So we're interested in starting here, understanding how the conventional systems in the literature work and how the new systems work and what's different about them. So I'd like to start at the beginning. So in 1989, I understood that the implication of the experiment was since there's no energetic nuclear particles, the energy had to be going someplace else. If that someplace else was vibrations or plasmons or some outside degree of freedom, that implied that the large quantity had to be fractionated. In 1989, I had no idea whether that was even possible. I had no idea how to do it if it was possible. And didn't actually have a good way to proceed. So as discussed yesterday, the approach taken was just to pick one model at a time, analyze it, try to learn from it, pick another model. And through 150 models, a lot of years until I found one that seemed to work. However, in the process, we started looking at specific models. And after looking at an example after example after example, it became clear that the details of the specific models were probably not what was important in this problem. What was important was the mechanism, and the mechanism could be understood and isolated in terms of more abstract models. So instead of working with D2 and helium-4's specific states, we could have one level for an upper state, one level for a lower state, and it would be generic and it would apply to all cases. Instead of having a phonon system, a plasmon system, very specific condensed matter systems and specific vibrational modes, the idea was to replace it with a generic oscillator. And so that would stand in, still allow us to describe the mechanism, but would free us of the details of the specific system, which might either be distraction or have complications in the analysis. So the way these models are constructed is through a Hamiltonian. The mathematical techniques to analyze these systems are taught in quantum mechanics classes and field theory classes and things like that. My purpose here is not to bore you with any of these particular approaches and method of analysis techniques. However, the thing I want to point out that's really nice about the formalism is that you know Hamiltonian. When you write out the Hamiltonian, you get to see what's in your model. So, for example, we can construct a Hamiltonian as a piece associated with two-level systems, a piece associated with the oscillator, and a piece associated with the coupling. So if you stare at the Hamiltonian, then you can see what's in the model. And in a sense, we're becoming lots of slides. You have to have some confidence that between me and my colleagues and textbooks and physics in general, that we actually know how to do some analysis of these Hamiltonians so we can analyze them and get an answer. So in case of the two-level system, the idea is that your generic nucleus or atom or molecule of a physical system tends not to be a two-level system. It tends to have lots and lots of levels. And the idea is that if you make a two-level system approximation, choosing two of these levels to focus on, kind of like forgetting about all the rest of them. And that has the big advantage, it makes your math much, much simpler. You have an oscillator. And if you think of an oscillator, think of like a pendulum. And it turns out that quantum mechanics oscillators describing wildly different systems, sort of in their guts, they work the same. And they're particularly simple algebraically. So having an oscillator means that you get to have the amount be really simple. And here's the coupling term. We can put in whatever coupling that we like. In quantum mechanics business, there's some rules as to how you ought to do it in order to be able to have a system that's physical. And the coupling basically says that if you want to raise or lower the two-level system, that gets coupled with either raising or lowering the oscillator. You might say, well, if you raise or lower, don't you have to raise and lower this in order to be an energy balance? And the coupling terms have no requirements for energy balance. Ultimately, we're concerned with something closer to momentum. The energy balance comes when you analyze the dynamics or the states and associated dynamics of the Hamiltonian. Quantum systems can be in energy balance or they can be out of energy balance, either temporarily or if they're pushed out of energy balance, pieces can be out of energy balance, pieces can be in energy balance, so you can have off-resonant pieces. Not overly intuitive, but it comes with the formalism. And there's more than enough experimental evidence to show that the world is consistent with this kind of description in the regions where it's applicable. Okay, so here's our first relevant Hamiltonian. It's a Hamiltonian for something called the Spin-boson model. Turns out to be an extremely famous model in physics. It's one of the ones that's best studied. What's in it is a term in the Hamiltonian that talks about two-level systems, talks about the energy. So in the upper state of two-level systems, you get more energy. If you're in the lower state, you get less energy. It's got a harmonic oscillator. Here's the coupling between them. So these terms written out are this. So we have a piece for the two-level systems, that's this. We have a piece for the oscillator. Here's the oscillator. Here's the frequency of the oscillator. And here's the coupling. So this is the coupling term. And the coupling term says you can destroy or create an oscillator quantum. And this thing says you can raise or you can lower a two-level system quantum. So what's in the model is exactly what we've been talking about. There's no more, there's no less. And that's the cool thing about the Hamiltonian formulas. And you write down the Hamiltonian, you get to see what's in your model. And that's a gigantic advantage. This is very famous physicist, recent Nobel Prize winner who did a lot to popularize the Spin-boson model. It had the earliest version of it dates from the time of Bloch and Seegert looking at NMR experimental work. And so that was a semi-classical version, and the quantum versions were looked at in the 1960s and 70s and so forth. Let's face up to it here. Here's a horrible brute force calculation of the effect under discussion. So what I've done is I've put the model onto the computer. I've diagonalized the system, got my states, I've made up wave packets for the states, and I've done it in a certain way such that it shows the effects. So in this case, I'm starting with the two-level systems, which are mostly excited. I'm starting with an oscillator that has an awful lot of quanta in it, but it starts out otherwise relatively unexcited. So the energy from the two-level systems de-excite, the oscillator excites, the two-level systems get the energy back, the oscillator releases the energy, and this is a process that takes sort of forever. It goes exceedingly slowly on a time scale for this particular model, but this is a numerically exact calculation of the effect. In this particular case, there's 200 two-level systems, and it's exchanging quanta, 17 quanta at a time. So the two-level system is 17, the dress two-level system is 17 times more energy than the oscillator's got. So it's an exact resonance at the 17th harmonic. And the two systems with the simple linear coupling is exchanging energy back and forth. And it's happy as a clam, and this is coherent energy exchange. And this is the basic effect we're talking about. And it's predicted by one of the most famous simple models that's relevant that's in the literature. There is no question that there's an effect of this sort. This is the kind of thing that we need, in my view, to account for excess heat in the Fleischer-Pons experiment. And this model, this kind of model would do the job, except for the fact that it's a little bit too weak. Let me pause for a moment and entertain thoughts, comments, or questions. Anyone have any thoughts? Okay. So, takeaway message. We've got the simplest possible relevant model. We've got sort of an abstract description which allows us to focus on the mechanism, the math, and dispense with anything that might distract us. We have a model that's exceedingly well known in the literature. It's exceedingly well known in the literature that it can exchange energy coherently in a multi-quantum regime. And there's experimental verification that this occurs even with a few dozen quanta being exchanged between the two-level system and the oscillator. Questions? Okay. Now, this is all well and good, but we have a large quantum, a dozen coherent energy exchange with a dozen quanta being exchanged isn't going to do us a lot of good for a function of quants. We need to go more. So the place to start is by asking some simple questions. For example, how do things work in the spin-boson model itself? And since the spin-boson model is showing an effect, but it's too weak, why is it weak? If we knew why it was weak, we might be able to fix it, make it stronger, and get a model to do what we need. So, first question, how does it work? Well, if you like, you've got a two-level system that can go up and down. You've got an oscillator that can swing more or less. And you have a system that can just simply exchange quanta back and forth that can raise the oscillator, lower the oscillator, raise the two-level system, lower the two-level system. So as a quantum system, it does everything it can and it accesses states that are not in resonance energy-wise. And basically, the system, according to the models, calculations, analytic numerical calculations, it basically keeps exchanging quanta between the oscillator and the two-level system again and again and again and again. It does it sequentially until it's exchanged enough to have the energy match. And when the energy match, then the phases come back into dynamics, come back into phase, and it's happy and it builds up some population density and it works. So there's nothing mysterious about it. If you keep on exchanging quanta and if you can maintain coherence, and if the system dephases, then you're done and it can't do the job. But as long as you can maintain phase and exchange the quanta, you're going to transfer energy. And that's what the models say, that's what it does, that's what the solutions say. We can look at it in yet another way in perturbation theory. Perturbation theory says, well, if the coupling is weak, you can get an analytic estimate by figuring out which states couple to sort of what contributions turn on first as the coupling strength increases. So the idea is we're starting with one state, so the system can have one level of excitation, two-level systems, and some number of oscillator quanta. And then it starts exchanging oscillator quanta two-level system, and it's going to go through all kinds of states until it, in this case, gets to a final state where there's one more two-level system and 5 less oscillator quanta for this particular example. So this is an exchange where the two-level system requires 5 oscillator quanta to be excited. So it's coherent energy exchange with up or down conversion of 5 quanta per two-level system. So in order to get from here to here, if you like, if there were a direct path between here and here, then we could calculate the dynamics pretty easily. We could say how fast is the energy exchange. And I'm imagining that in the general case, this is much bigger and there's more states and there's more fractionation. So this is sort of something simple that I can draw and think about and analyze. In perturbation theory, I've got a scheme where I can calculate, I can estimate the indirect coupling from here to here. All I have to do is to add up the contributions of each of the different paths independently. So I can add up this path, add up this path, I can add up this path, this one. So I go through and I add up all the different paths and weight them according to the rules given in the perturbation theory. And what I find is that when I sum them up, they tend to cancel. And it's a destructive interference effect. One's going this way and one's going this way. I contribute with a different sign. It's roughly the same number going this way as going this way. The weights are roughly the same. And the cancellation is astonishing. Even for this simple case, you can get parts per million result due to a cancellation of 999,999 of the other parts. They just cancel out. So the reason that you can't fractionate a quantum with a spin-boson model is because the spin-boson model has a destructive interference effect hiding it. That's what limits things. And it's along those lines. If you have some magical way to eliminate the destructive interference, even in the simple model, you would get like 1,000,000 times faster energy transfer. And in bigger models, you would be able to get plausibly fast energy transfer under conditions that are not overly heroic. So this destructive interference effect, that's what's standing between us and the sensible, rational, logical physics explanation for cold fusion effects. Comments or doubts or questions so far? This is like an important point. All right. So that's what I've said. So that after looking at 150 models that didn't work, and in the process of beginning to think about writing up an explanation as to how this is just impossible, an impossible problem. Is it possible to fractionate a large quantum? I was going through all the special cases I needed to do to be complete, and one of them involved loss. When I thought seriously about the loss business, it occurred to me that loss had the possibility of breaking up this destructive interference effect. And on the one hand, it's sort of subtle. On the other hand, I guess retrospectively, it's really obvious. But a simple way to think about it is that the system's got, let's assume the system has an energy plus to this line right here. And we're trying to make up the quantum state. The quantum state's made up of all these different basis states. Now, basis states have different energies. It's got lower energy, higher energy. In the presence of loss, again, it depends a little bit on the details of the loss, but you can imagine that if you're hanging around a state like this, if you've got this much energy, and there's a basis state that looks like this, if you dumped this much energy, this guy is potentially something like a candidate state for a final state for a loss process. And so giving up energy, the more energy that you give up, generally the faster your loss process is. This guy could also be a final state for loss process, but this guy has more energy than the energy the system has available. It's possible to have a decay process where you suck energy out of the system in order to decay. It happens all the time and is well known in physics. The only thing is when you suck energy out of the system, it turns out that it makes it much harder to decay. So decay process is where you're going to the final state that has more energy than the system has in the first place. That's not an easy thing. Not an easy thing to do. I guess if we were really precise and said this is all the energy available and if this exists in isolation, then it would even be disallowed because you couldn't get there. But thinking a little bit more generally about this kind of problem. So along those lines, if you add loss to the system, then the states down here, the basis states down here, as they're connected with the system, are states that in general are going to see higher loss. The states that up here, they're going to be states that see lower loss. And if the states see higher loss, then if you're running through a pathway here to try to get here and you lose some of your population before you get there, well, it's not going to, the amount that was busy contributing to destructive interference, if there's less of it, it's not going to be able to destructive interference as much. And that's the brainstorm as to how and why loss can break the destructive interference and result in a greatly enhanced capability of the model to fractionate a quantum, or to go from here to here and exchange energy coherently under conditions of massive outconversion. In terms of the spin-boson model, they have to add a loss term. And back in those days, I said, let's go ahead and add some loss to it that sort of works this way. And does this kind of thing. Not too terribly difficult. This kind of model for other applications is well known in the literature. When I plugged in this kind of loss and started calculating, all of a sudden I started finding models predicting very high coherent energy exchange rates under conditions of fractionation. I mean, it's sort of astonishing. The first day I discovered it and I had codes up and running, very quickly they were showing me very large enhancements of the coherent energy exchange rate. Since that time, and that was back in 2002, since that time we've got perturbation theory models, we've got strong coupling regime results, we've got analytic results, we've got numerical results. These days we've got an approximation scheme. It's called the pulse amplitude approximation. And it gives answers from really trivial kinds of constructions that match very well computer calculations involving lots of states and burning up lots of computer time and so forth and so forth. So at this point, we've come at it from a lot of different directions, and all of the different approaches used on this model to analyze this model shows that it works. We succeed in eliminating the destructive interference. And we get large enhancements in the coherent energy exchange rate under conditions of fractionation. Okay, take away this. I'm thinking about your model message. Comments or questions or thoughts?
Can we talk about loss for a second?
Sure.
Does that mean a sample that heats up? Does that mean a sample that is heated up and you remove heat from it? Or both, or something else?
Your question's a fantastic question. And I've been interested in this question for a very long time at this point. Years and years ago, I thought, well, the loss that's important is the off-resonance loss in the vicinity of the transition energy for the two-level system. So that was the story. When people had asked me all these years, I'd say that was it. So if your oscillator is oscillating at one frequency and your two-level system's at 10 times that frequency, then I would say the loss at the one frequency is not so important. The loss at 10 times the frequency is the stuff that matters. Now, that was true, and that was my story up until I had some more sophisticated models where I could put in different loss models and check to see where the loss needed to be and what difference it made. When I got the new models up, I put in some loss near the delta E transition energy, and I saw the effect and it worked. I said, well, suppose I put it twice that energy. Well, it took a little while longer to turn on, but it worked too. I said, well, suppose I put it at a couple of photons worth and don't go out to delta E. Does that work too? That seemed to work. I said, well, let me put some loss at delta E, at the phonon frequency, vibrational frequency. Turns out that worked as well. So we'll talk a little bit more about it. But the loss at this level, it turns out that these models, the effect seems to be pretty robust, and the requirements on loss are not particularly stringent. However, in detail, in the different experiments, there's different kind of loss mechanisms. So in the vibrating copper foil experiment at the moment, I'm thinking that the loss due to coupling to conduction electrons is the loss that's really important. In the Fleisch-and-Pons excess heat business, I don't actually know at this point which loss is the dominant loss, but I'm of the opinion that coupling to the conduction electrons is going to give loss, which may well be sufficient to do the job. There's also loss associated with ionizing inner shell atomic electrons, and there's also loss associated with promoting nuclear excitation and disintegrating nucleons. So there's like 3 different kinds of loss, and from what I know from my studies so far, all of them are capable of contributing. In order to figure out which one's the most relevant, most important, I got to go in and exercise my models to check one after the other. The other is not even understand. Fantastic question. I wish the answer were simpler, but it is what it is. Let me talk very, very briefly about sort of how fast the energy exchange is. So, for example, we've analyzed the model, we've analyzed it in the strong coupling limit. And there are papers on it which describe all these results in detail. And this model also, again, for purposes of clarity, focuses on the maximum rate of energy exchange. There will be other models which we'll talk about that can go between minimum rates and maximum rates and describe something more general. But this is a result from the maximum rate, and basic idea is that if you put things together, you get a limit where things are working really well, and the energy is going from an oscillator to two-level systems and two-level systems and back. The dynamics is basically a funny, ugly, nonlinear oscillator. The energy, the two-level system energy starts, it's going along, and also burps, and it goes down, and the oscillator gets the energy. It goes along, and it burps the other way, and it goes this way. So this is the kind of dynamics described by this. And so we can actually figure out what the speed of it is. And I've written it in a form which may look colorful, but probably doesn't mean anything. But it turns out there's some intuition to be had. The thing in green here is basically the Rabi oscillation frequency for this model. So this means that if you were exchanging one quantum and everything were resonant precise, if there were no fractionation at all, but you had this kind of coupling, then this would be the rate at which the energy would go back and forth. So this rate right here, think of as being fast. This is sort of the standard fast version of the problem if there were nothing else to it. This guy right here is a hindrance factor. So it basically says that if the coupling's strong, then the energy can be fractionated. If the coupling is weak, the energy can't be fractionated. So this factor looks something like this. So here's the argument. It goes down to diddly squat, down to 0 if the coupling's weak. If the coupling is sufficiently strong, it's going up somewhere near 1. So this is basically a switch that turns on and off, and it says coupling's strong enough, then yes, you can get the fast rate. If the coupling's not strong enough, then no, you can't transfer the energy. It's not going to happen. You're not going to allow it. And this final term is a dilution factor. It's an algebraic dilution factor that basically says if you want to exchange a lot of quanta, well, there's going to be a tax, there's going to be a price. Your rate's going to be slow. So if this were 1 and this were the Rabi rate initially, for 1 quantum, well, if you go to 3 quantum, for example, if this formula applies, it's only very, very approximate in this case, then your rate would drop by a factor of 9. If you wanted to exchange 1,000,000 quanta, then your rate drops by 12 orders of magnitude. And you could say, that proves this will never work. If you want to exchange 10 to the 9 quantum Fleisch and Pons, you're down by 18 orders of magnitude, you're dead, it's hopeless. Well, it turns out that this number can be big enough in all of this that you can still get a finite reaction or finite coherent energy exchange rate, even under conditions of massive fractionation. And that's really, really interesting. I guess the several takeaway messages from this. One, we can formulate the model, we can solve it in a strong coupling regime, we can get scaling laws, and the results of scaling laws basically say that the penalty for fractionation is algebraic, and it's not particularly strong algebraic penalty. And that's big. And this result is the result that says, yeah, we've got a real chance here of fractionated quantum connecting with the Fleisch and Pons experiment. That was the significance of the brainstorming the model and so forth. We have our very first theoretical mathematical existence proof of the possibility of being able to do what it is we need to do to make sense of the experiment. Answer questions so far.
is sort of a first hurdle. Model has to be able to do this before we want to push it further, right?
If you like, you can say it's a first hurdle. In my view, this is also the biggest hurdle.
Okay.
In fact, when we first got these results and I was staring at them, I thought, oh, we've got the answer. We can model it. Silly me. I suffer from this like incurable optimism.
How else are you going to do this for 25 years?
Say only 25 years. It doesn't sound so bad that way. It's only 25 years. Okay, so spin-boson models capable of coherent energy exchange for CD. It's the limiting is due to destructive interference. Loss eliminates the destructive interference, gives us this new lossy spin-boson model that's capable of fractionation. Stronger coupling gives us more fractionation. Stronger microscopic coupling allows it to work better. And this model is also interesting because it's enhanced by having more two-level systems. So for example, if your coupling is really, really weak, I'm saying, it'll never work. But if I add 10 more two-level systems, or 100 two-level systems, 1,000 two-level systems, that boosts the fractionation power. So it turns out that associated with these models is a requirement of having a lot of these guys together, working together in order to fractionate the quantum. And then that's shown up in the modeling and analysis and so forth. A very tiny system is going to have trouble. A tiny system with few two-level equivalent two-level systems is not going to be able to fractionate a very big quantum. But if you have a very large number, 10 to the 23 or something, then your ability to fractionate a large quantum increases dramatically. And as we noted, the scaling law allows for modeling and predicting a strong coupling regime with fractionation on the order, for example, of 10 to the 9th quantum. The idea is that these models really are up to the job of describing the kind of stuff that we need to do. And a discussion involving a frighteningly large number of quanta is no longer an emotional discussion. It's a discussion where we can pose the problem. We can say how strong coupling we need, how many two-level systems we need, what conditions it works, and how fast it goes. So it's now a question of mathematics and model rather than a question of intuition or belief. Anyway, take-away message. Thoughts? It's early. My head's pounding from a wild night of making slides. Okay, I want to talk a little bit about a more sophisticated model. Okay, the result discussed so far is significant for the reasons outlined. All the subsequent theory that I'm going to be talking about today rests on this kind of result. It provides a mechanism for fractionation of Flushing ponds, and for other things, we kind of like to be sure that it's right. So for example, if somebody does an experiment and it gets an important result and a lot's resting on it, you'd like to have somebody else do the experiment, say the same thing. You'd like to have 10 labs all get the same thing and measure it to precision. Well, for a theoretical result, in a sense, the same kind of thing holds. You'd like to be sure that the effect is real. And one way to do it, actually, before we get to that, I have colleagues that are absolutely sure that there's a mistake in this lossy boson stuff, that it's not possible to fractionate. Also, from my own perspective, the simple model that has been described and we're able to analyze so much involves a horribly crude approximation. I mean, not crude by accident, by default. It was a crude approximation that I put in, and I put in on purpose in order to give me a model I can analyze. So the crude approximation it's recognizably a crude approximation. And there is even reason on my part to be concerned with having such a crude approximation. So the idea is we have plenty of motivation to want to come back at this and see if we can, well, for example, if we can break it, that would be important. On the other hand, if we can confirm it, that would be important as well. Probably you guys know me well enough by now that I'm interested in knowing what the right answer is, whether it have to be a good answer or a bad answer. So breaking it would be, I would actually be happy if I could break it, because then I would know what the right answer is. It would be sad with respect to all the work that's gone into it, but that's the way it works. I want to know if it holds up or whether it can be broken. If it can be broken, I want to be the one to break it. Anyway, so destructive interference is the big deal. The early modeling said less important as to how you break the destructive interference. So the idea is that in the early models, I put in different loss models. So I got roughly the same coherent energy exchange rate, sort of independent of what kind of model I used for loss. So that suggested that what I should do is to put in a really crude model that said the decay rate for all of the states that could possibly be candidates for having an enhanced decay, let's make it infinitely fast. And everyone that's a bad candidate for decay, let's make it 0. So if you do that, you end up with a model that's, again, it's very crude, it's very dumb. It's like taking a hatchet, going in and whacking away. But it also gave me models that I was actually able to analyze and get answers and get limits, as you've seen, get very accurate answers from. So the approximation is very crude. The analysis is very precise after that, because the resulting math problem is easy. However, now, more than a decade working on this model, and the questions come up many times, are we sure of the model? How good is it? We've always recognized the need to come back and test it, do better. So crude models got infinite loss. What happens if the loss is finite? The crude model gives you the rate at the maximum, it gives you the maximum coherent energy exchange rate. But we'd probably like a model where we can start with loss that gives no enhancement of the coherent energy exchange, and then turn loss on a certain way and see it come up. We'd love to have a model that worked that way. We'd like to have a more sophisticated model that takes into account the spectral shape. So if we put loss in one place and move it over and put it in another place, can we get some intuitions to where the loss needs to be and how strong it needs to be in order to understand the impact on fractionation. So instead of having a crude model, we're contemplating now having a more sophisticated instrument where we can analyze things in realistic situations and do so systematically if possible. Well, the model under discussion is one that looks like this. So there's a lot of stuff in it. On the top line, we got our 2-level systems, oscillator and linear coupling. So this is the basic spin-boson system that we've been talking about. Here we've got a description of loss. So what this is these are 2-level systems, but they're lost 2-level systems. There's a lot of them that got different energies. The phases are going to destructively interfere. We've got linear coupling here. So we create or destroy oscillator quantum, we raise or lower the loss quantum, and we can weight it. So we can say, guys down here interact more weakly, guys here interact more strongly, these guys interact weakly. So in a sense, this what's under discussion here is basically a standard scheme for introducing loss into this kind of model. So in the literature, there are a ridiculously large number of papers with this kind of loss model. And there are even papers with this kind of loss model in connection with a spin-boson model as well. So lossy spin-boson models are discussed and analyzed in the literature. And this is reasonably close to, or very close to, the kind of models that people use for lossy spin-boson models in the literature. I will point out that as far as I've seen, nobody in the literature has been interested in the question of the impact of loss on the coherent energy exchange rate. I think Irfan and I are the only ones on the block that are aren't worried about this problem at this point. Anyway, so that's the model that's under discussion. We can specify the coming path levels. We can model a real system having some principle. Namely, tell me which losses you're thinking about, and estimate how strong the coupling is in density states, and so forth, and so forth. Model. In fact, this more general kind of model contains all the effects that anyone would basically need for an awful long time to come. This is a very general, very powerful model. But this model is now more complicated. Remember that Hatchet coming and making a crude simplification? Well, at least I can analyze it. Well, this one's much, much more difficult, much harder to solve. Okay, let me pause. Thoughts or questions, comments so far? What do you think about my new model? Like it?
It's where you gotta go next.
It is. It's the obvious thing.
Okay, so 30 plus years ago in hot fusion, so my pay for this, Kurt, we'd spend weeks where we'd go, I'd go, Kurt, is a billion zero or infinity today? And we work our models based on that.
You make progress in this business by you construct models, you analyze them, you look at the answers, and you keep on going. That's how you learn things. Okay, so
I have a quick question.
Yeah.
Has there been any attempts to or thoughts about trying to model your system more closely to what would actually be in a lattice of palladium deuteride or something?
this is exactly the kind of thing that's under discussion.
Yeah, 'cause
Namely, I'm trying to build up this fancier model. If you go ahead and you look at the palladium deuteride and you say, well, I've got conduction electrons and the photons can couple to the conduction electrons. Well, I can model the conduction electrons this way, and I can model the coupling this way. And if you say, well, I can promote inertial electrons, I can have my inertial electrons model this way, do the coupling this way. So in principle, this gives me the framework where if I have all the numbers, be able to analyze it, put it together, I can put it in, I can grind it out and check detail against detail against a real physical model. So has that been done yet? No. There has been the beginnings of attempts to put in realistic models for different physical systems and try to begin to analyze and sort things out. In fact, I made an awful lot of progress in one I was very interested in late last summer.
the results you got from those fudge numbers that you put in were pretty interesting. So
Okay, so so now we've got a more complicated model, and how do we proceed? With a more complicated model, there's sort of a very old approach that's sort of very simple, and it's sort of a perturbative approach. It's not a very strong approach, but it's easy to analyze. It's called Brillouin-Wigner. So I thought I would try that one first to see how it works. So here's a second order version of Brillouin-Wigner on that model. Here's a third order version of Brillouin-Wigner. There's lots and lots of terms. So I took all the terms and coded them up, put them in the computer, started solving away and grinding away. And what I found was interesting. The question is when you have one of these models, the question is, how good is it? So the idea is that Brillouin-Wigner, I know is good for weakly coupled systems or easy kinds of systems. But it's also sufficiently simple that I could implement a version for the industrial strength systems, and if it would work, it would give me a predictive tool, and I could start solving things systematically. But I got to start somewhere. So here's sort of an exact model calculation with the full Hamiltonian under simple conditions where I can grind it out by brute force. So here's the answer. I compare this with the Brillouin-Wigner, and here's the Brillouin-Wigner. Go back and forth, back and forth, back and forth, back and forth. You can see they're basically the same. So Brillouin-Wigner is actually able to get me a good answer. In fact, this is interesting because in this region right here, you get spin boson low levels of coherent energy exchange. And here's where things kick in such that the loss is turning on and starting to make it be bigger. So you can go in and you can see it going from no effect to beginning to turn on. There, it's turning on, and it turns on in the full model. It turns on in the Relativistic model, and at the moment we're happy. We can see it begin to turn on under very simple conditions. We've got a number of these calculations, and they sort of all work qualitatively pretty similar. So the assessment so far, we've got our first result. Minor technical issues, second, third order models are very fast. They give a good answer to the third order model, and this problem gives exactly the same results. It looks really nice. Let's do a little bit tougher model. We're going to now vary the coupling strength. So this is sort of weak coupling. This is intermediate coupling. Strong coupling works way the heck over here. So this is the full brute force, take the whole Hamiltonian, plug it in, and just start hammering away at it and get some answers. So that these are the exact answers. Now let me take my Wigner, my cheap, simple model that could actually have some chance of running for bigger systems, and try that, and Shazam. Go back and forth. Oops. So full model for Wigner. So in this region here, I'm getting the same answer. So there's a regime where Wigner is working, but here that doesn't look at all like what's going on. And so what I'm finding is that Wigner is an approximation. It keeps some terms, leaves some terms out. So here are the terms that kept, they work. Here are the terms that left out. Well, they're not there, so these things don't go all the way over, and it breaks. So sadly, my Wigner, which I had such high hopes for and I wanted to work, it's failing me here in this region. I can't get good results systematically everywhere. So that's too bad. I actually spent some time looking to see what I would need to fix this. So I found that for this particular problem, if I go up to fifth order, I could actually fix that and have a model that would work, and I could plot something that would be in agreement. And fifth order, I end up with like 120 terms or thereabouts that I have to put in code up, and it would take an awful lot of work. But I thought, I'm willing to do it if all I have to do is code in 100 some odd terms, and I can get a model that will work and be happy as a clam. The only thing is that this is delta n equals 3. If I go to delta n equals 5, then the fifth order terms aren't going to be enough. We need the seventh order terms, and there's like a couple thousand of those. And if I do bigger delta, I'm going to need more terms. And pretty soon I'm talking about putting in 100,000 terms. At some point I get tired. I do have a line I'm going to draw somewhere that I'm not going to be willing to do to test it out. So the answer is that I can do something with these kinds of models, but it's not good enough for industrial strength calculations for where I want to go. The good news is that easy problems can be done this way. The bad news is, in the regime that I care about, the Wigner approach, it fails. It doesn't work. Take it out in the back, dig another grade, vary that approach, and move on. Comments, questions about this so far? All right, so pick yourself up, dust yourself off, try again. Had high hopes for Wigner, but not strong enough. Before, with the lossy Spin-boson model, I had a lot of luck with something called the local approximation. So I thought, let's try the local approximation in connection with these models. So first try for the local approximation. The blue is the local approximation calculation. The red is basically a perturbation theory calculation, which is sort of, in this case, in this instance, it would be considered to be a full model calculation, including everything. And the difference here, this is, my numbers only have a certain number of bits, so what's going on here is these are both saying the rate's very small, so I'm not worried about here. In this range, this goes up, this goes up. The dots are reasonably close to one another. and they're close enough to one another that I look at this and I say, aha, at least in this regime, the local approximation it's basically working. It's not perfect, but if I could get systematically results this close, I would actually be exceedingly happy, and I could begin to use it for design analysis. And I wouldn't be as happy as I'd like to be, but I could make progress with that. So I thought, let's go ahead and try this systematically. Let me try the local approximation with the Brillouin-Wigner kind of expansions. I know it's got headaches, but let's try it anyway. People do this kind of thing. And what I find is that for the simple version, I'll look at the blue. For the second order Brillouin-Wigner, I get red. For third order Brillouin-Wigner, I get this cyan kind of thing. And looking at that, the first two of these, the fact that they're sort of close to one another, I say, well, okay, that's good. That's sort of what people in the literature for this bad kind of approach would find. But the fact that this one is off by like, changes by a couple of orders of magnitude, adding the third order terms was supposed to be a small term in perturbation theory, so it was supposed to make a small difference, but here it's making a big difference. So what this is doing is waving a big red flag saying, look, I'm breaking, it doesn't work. Don't use me. So the local approximation coupled with this kind of approach fails. The local approximation itself works okay. It's fine. If I could implement it systematically, which is sort of hard and very expensive, I could get good results, but any cheaper version of it just simply fails. So go crashing down in flames again, go out in the backyard, bury another dead model, and see if I can figure out a better approach. Comments or questions or thoughts so far? Anyway, this approach isn't working, so one more try. The research from the beginning has been a set of you try something, everything fails, you try again, it fails. See Mitchell shaking his head, I guess it's that way in the lab as well. So thinking, I like the more sophisticated model since it's a better model. It can handle realistic loss profiles. It's clearly tougher to work with. And at this point, I need a stronger approach. I need a bigger hammer. So there's an approach I was thinking about. It's called an iterative loss approach. So this kind of headache with perturbation theory appears in other problems. In other problems, people have got solutions. So I thought, let me use one of these solutions. So one solution, which was natural for this one, is to try an iterative interaction to model the loss. Basically, you're trying to separate two degrees of freedom, and Brillouin-Wigner is good at that. If you carried out Brillouin-Wigner sort of to all orders, you get something that you can actually sum, and you can write formulas down and get an iterative formula. It's sort of the nature of it. People that work with it derive it in other applications. Don't reference it back to Brillouin-Wigner, but it can be. Anyway, so if I implement it, it gives me something that looks like this. It gives me a sort of a Hamiltonian that's got my spin-boson thing here. And now it's got a loss operator. And the loss operator, I have to calculate self-consistently from this iterated kind of model. So this is, if this were done properly, it would be an exact, it would lead to an exact result. In order to implement it practically, you basically have to iterate, and there's a lot of states. So I've got versions of it where I've made one approximation or another approximation. I've got a version where I've iterated to self-consistency as exactly as I'm able. So I've got different ways I test them against one another. And it turns out this allows me to begin to get some answers. So there's some progress to report. I'm going to defer the progress by introducing another issue. This might seem to be a tangent, but it'll place into context the solutions I found to make them more relevant, more important. So the question on the table, this is sort of independently. Over all these years, I've been arguing that if the loss is really strong, then you blow away the levels that are giving you the destructive interference. So the argument has always been that you really need very, very strong loss to get the fast coherent energy exchange to occur. So the question is how strong does the loss have to be? Namely, if I could get a criterion for how strong the loss could have to be, that would be a really important criterion, because then I could point at a system, I could say, this system meets the criterion, I know it exchanges energy in this new way. And another system, this system doesn't meet the criterion, it doesn't turn on. So that's the kind of thing that I'm looking for. I want a criterion as to where this new business turns on. And when it's going through the analysis, a relatively obvious criterion suggested itself. And it corresponds to a formula that looks like this, but it basically says, here's a measure of how strong the loss is, and here's a measure of how strong the coupling is. So I've got the coherent business, I've got the loss business, and I've always been arguing that the loss needs to be strong. So here's a formula that I was able to develop based on relatively straightforward reasoning and working with some numerical results. Under these conditions, what happens is the iterated loss gets localized. And if it gets localized, it means locally it's going to destroy the occupation states there, which by definition will ruin the destructive interference. So under these conditions, I'm absolutely sure that I'm going to get an enhancement. So when I got this together, I thought, well, let's check it out. And I'm able to run some calculations. Let's see how good this is. So I ran some calculations, and it turns out that this works. That if this is satisfied, you in fact will see an enhancement of the coherent energy exchange rate. In fact, you will get answers that are pretty darn close to what the crude model gets. So success of sorts. Now the only question is that I've got a greater than here, and the question is, does it work the other way? If this is less than, do I have a guarantee that if I have the destructive interference, I get a low energy exchange rate? So that's what to be tested. And what I found is that this is far too conservative. And not only is it conservative, but it's suggesting that this way of thinking might actually not be correct. So in light of this discussion, let me go and look at some solutions. So the idea is that in experiment, fractionation seems to turn on as you increase like the current density or you increase one parameter or another. In the model, in both the crude model and the new models, the effect turns on when you do the same thing. And what I'm hoping, what I wanted to get was a formula that says, here's where it turns on. So this formula was my first attempt to get a formula that says, here's where it turns on. So I have a formula that gives me a guarantee that it has turned on when this is satisfied. Again, which is useful and important. It's the first in the story. But the current constraints to restrict if this system seems to turn on earlier than now. I believe that I was convinced there should be a threshold. And in a sense, the models do give a threshold, they do give a turn on. But I was looking for an absolute one, and the model says it's relative. So the thought is now with the new model, let's just do lots of calculations and let's see what the model does. So here, so what I did is I said, let me put in some loss, which it's not a large amount of loss. It's some loss, and it's enough loss where I would think there'd be a reasonable chance that I would get an enhancement in the coherent energy exchange rate. So that's the yellow curve. So this curve, what it's telling me is that when I increase the coupling strength, I'm seeing an enhancement, and I'm going here, so it's actually getting up there in the general vicinity of free exchange, and very, very fast. In essence, so here's my yellow line. I put in a loss, which is not an overwhelming amount of loss. I put it in, like two phonons worth or two oscillator quanta worth. A little bit of loss is just sitting there. It's not doing a whole lot, and it's basically working. So I say, I want to make it not work. So let me take it. Let me cut its amplitude down by a factor of 2. I'm going to cut down the loss by a factor of 2. So that takes me to the green. Didn't get rid of it. Let me turn it down by another factor of 2. I get the red. You turn it down by another factor of 2. I get the black. It's not going away. And I was hoping to have it go away because the amount of loss that was in there was a very, very modest amount of loss. I was even at the point of being surprised that I was seeing an enhancement. Last time I presented this, I was arguing, I said, well, somewhere over here is the limit of infinitely fast, the limit where the loss is infinitely fast. So we could compare it against the maximum. I didn't have it last night, burning the midnight oil. I thought, let's get a plot. We want to see that plot. So here it is. So this is the result from an earlier crude model. So this is the basically coherent energy exchange rate working as fast as is conceivably possible with no destructive interference whatsoever. And I get a curve up here. And I'm looking at this, I'm looking at this. So infinite loss, distinctly finite loss, very, very modest loss. So how do I think about it? Well, the way I'm looking at this is I'm thinking that if I don't have infinite loss that's going to blow away half the states that are contributing to destructive interference, I can still make things work, but what I do is I push it off in terms of the coupling strength. So, for example, at this point, going from here to, I don't know, here, around here, that's an order of magnitude in coupling strength. So if you think about it, if I'm down here, basically that's somewhere close to where I would say that it is starting to turn on. And it would turn on at this coupling strength. But if the loss is much weaker, then it turns on with a delay in the coupling strength. Basically, it's telling me I've got to put in 10 times more of these two-level systems to see the fractionation under conditions where I don't have maximum crude sledgehammer kind of loss. Let me pause for a moment. Comments or thoughts or questions?
The whole idea of this coupling thing that you're saying is going on in your model is kind of, I feel like it perhaps agrees with the thing you had about the super waves, shocking things with the super waves, because you're essentially resonating lots of little things in some way, right?
Well,
Is it related at all?
No, the super waves is related to the flux. The flux was giving you excitation, and more excitation would sort of move you in this general direction. So there's sort of a connection there, and actually probably the right connection as well. Other thoughts or comments? Anyway, I'm looking at this result, and I'm basically coming away flabbergasted, thinking I didn't really understand this model. I was looking for it to turn on. I wanted things to be black and white. I wanted it to be either on or off. The system didn't work or does work. And so far within these models, that's not really what I'm finding. What I'm finding is sort of shades of gray or something. If I put in a model which I didn't think would work very well, turns out if I make the coupling strength larger within the calculations so far, it seems to be working okay. Just it's harder to get it to work, but it can still work. Also, I can see conditions under which there's basically no effect at all. These kinds of models are going to be going over the range from not working to working as good as possible. So an unsophisticated model, which should have this capability, is starting to look like it does. And that's interesting. Okay, so anyways, this is what I've been talking about. I guess there's two bottom lines from this. One is that I'm seeing coherent energy exchange enhancements, not yet under conditions of fractionation, so multi-quantum, sort of closer to, instead of 10 to the 9th, I'm still down at modest number of quanta for these calculations, and I don't have scaling laws yet for the new model. But so far, it's very interesting. It's providing sort of a confirmation, at least in a regime that's an interesting regime. I'm starting to see the effect. And it also is suggesting that the fractionation business is a little bit more robust of an effect than I had been expecting so far. Anyways, this is opening my eyes. What remains to be done is to get a more systematic parameterization, to get the scaling laws general for this sophisticated model, but that hasn't been done yet. But if it could be done, we would be in a position of having a much more powerful version of this model that would be able to be applied to experiment much more systematically. All right, are we ready for the sort of the next step in the argument? I want to begin thinking about application models to experiment. So the basic idea is that the hardest feature of the experiments of Fleisch and Pons was the absence of the energetic nuclear radiation. And from my perspective, that means you have to be able to take a large nuclear quantum and fractionate it to a lot of small condensed matter-sized quantum. We now have a mechanism that looks like it's able to do that. So the question is can we take the mechanism now and begin making connections with particular specific experiments? Instead of having things be all abstract, can we go back and say, let's take a D2, let's take the helium-4, let's take the lattice, let's do the coupling, let's roll up our sleeves. I'm not going to, it's too cold here today to roll up these sleeves here. But let's roll up our sleeves and see what we can do. Now the headache is that the simplest version of the model, even though it's conceptually simple, it's not so closely connected to experiment. Let me show you what I mean. So the simplest thing I could imagine is let's start with coupled in helium-4. So I got a two-level system, I got a transition, I got some coupling, I can exchange a vibrational quanta with a highly excited phonon mode. And I've got a model which would basically correspond to velocity spin-boson model or correspond to this fancier version of it. So I now put everything together, I have some ability to analyze it. And when I analyze it, I come to the conclusion that the matrix element from going here to here and coupling a phonon out is very, very, very tiny. I need strong coupling to fractionate a big quantum. This is not going to work. And so this doesn't work. So what's conceptually the simplest and most straightforward application model, namely, let's just do cold fusion, let's turn D2 into helium-4, let's give the energy to the vibrations, let's fractionate it. You know, it'd be a great story. I could explain this really simply, but the math just doesn't work. I mean, I'd like for this to work if it's going to work, but it's not working. And this says it just doesn't work. We talked last time about basically inverse fractionation to vibrate something to excite level in mercury 201, and we were arguing about connection with carbon collimated X-rays. So I can similarly say, well, let's imagine that we got mercury 201 ground state, and I've got coupling to the excited state, and I'm going to actually, instead of going down, I'm going to go up this way, but I'm going to exchange energy between this transition and the vibrational mode. Once again, I can look at this and I say, lossy spin boson. I should be able to inverse fractionation go this way, or do fractionation go this way. The model goes one way or the other, sort of on equal footings. They're very closely related as we expected in the first place. I can analyze this, I put it together, and I come up with a headache that in the Harwood experiment, if there's mercury on the surface of the cathode, it's only there's an impurity. There's not very many of them. So the coupling is weak. I mean, I'm not Coulomb hindered this time. The core matrix element probably is sizable. It's not Coulomb hindered by 10 to the minus 40 or something. So in this case, I've done a microscopic matrix element that's reasonable, large enough to begin talking. However, I've got so few of them that the coupling with respect to the velocity spin boson models is way too weak to fractionate the quantum going up and down. So once again, I got a beautiful model and explanation. It just doesn't apply to the problem. And once again, this is very sad. I'd be much more successful in explaining how these things work to the audience if I had simple models that would do the job of the work. I've actually proposed that it might be possible to set up a version of experiment where this might apply. It's a horrible experiment. It would involve frozen solid mercury being vibrated. I wouldn't want to be anywhere near the lab where that got done. So it's not strong enough. So as a result, we're going to have to do something different. If you like it, it's one of these situations that Mother Nature's throwing me up against the wall and saying, look, it doesn't work. You have to do something different. So kicking and screaming, being very unwilling to take the next step, I'm going to go do something different. I hate more complicated models. I hate more moving parts. I hate harder models. But in this case, I have no choice. I'm not going to make any progress with the simplest version of the model. The brainstorm back in 2002 was to work with a weakly coupled transition, give the energy to a strongly coupled transition, let the strong transition do the fractionation, which would look from a distance as if this one was it's taking advantage of it. So this guy's not doing the fractionating. The strong transition is going to do the fractionating. But within these models, it's relatively easy to shift the excitation over from one place to another. This is called the donor and receiver model. So pictorially, for Fleisch-Pons, it looks like this. A D2 to helium-4, weak transition. Somebody else over here, strongly coupled transition. At this point, don't ask me who this is, because this was a problem that took more than a decade to sort out, but we'll come back to. So we can set this kind of model up. And it turns out it's easy. So here's the spin boson model. I can add my crude loss, or I can replace this with my fancier, more delicate loss model, more sophisticated loss model. Here's the, actually, this guy, and this guy would be the spin boson on the weakly coupled system. This guy, and this guy would be the spin boson for the strongly coupled system. Here's my loss to make everything lossy. So here's the kind of model that implements what's under discussion. And if I use the crude version of loss, then I can analyze it systematically and I can get answers on it. And this is interesting. So I can use this now to connect this kind of model to Fleisch-Pons excess heat effect. So the idea is it works this way. D2 goes to helium-4, one step, one transition, very slow, but coherent. The energy is exchanged to here and it goes over here very easily, sort of very quickly. And over here it goes up and down, plays patty cake with the oscillator, and it fractionates the quantum. And you can put together the model, you can analyze it, it works well enough. And you have a limit, and the limit that the fractionation is efficient, so that the bottleneck is going from the fusion part of it is the bottleneck, the D2 going from the port, that's a bottleneck, then you can get a rough estimate for the rate at which the reactions happen. And you can plug in estimates for these guys. I'll talk more about that later on. But what you find is that the rate ends up basically being within the realm of the numbers from experiment. Anyway, you can get consistency between this model and experiment from, you put in the best numbers you have for the number of D2, the size, the frequency, the oscillator, the excitation level of the oscillator, and you put it all together, you can get self-consistency. Now, mind you, in all of this, the problem of the Coulomb barrier one of Heisenka's first miracle problem, how do you overcome the Coulomb barrier? Well, here it is. You don't. The Coulomb barrier is there. You tunnel through it just like you'd calculate it with an honest calculation. All that happens in this model is that it comes in only once. You get e to the minus big G gamma factor. Whereas in the incoherent process, it comes in as that factor squared. So given that e to the minus G is like 10 to the minus 37 or something, so e to the minus 2G would be 10 to the minus 34. There's also a volume factor shows up. So having one of these things rather than the square of them is an awful lot of orders of magnitude. And those orders of magnitude are basically all you need to get reaction rates to be consistent with the experiment. You don't need any heroics about making the Coulomb barrier disappear or anything. And that was the motivation for chasing after this kind of theory in the first place. But a coherent theory, a coherent process has a maximum reaction rate that's linear in the matrix element, whereas an incoherent process has a rate which goes like the square of the matrix element. In this particular case, that makes all the difference in the world. Let me pause and entertain questions or comments. All right. I see what's exhaustion on your faces.
No, what dopant should we add as a strongly coupled system?
Let me continue on.
Sorry, I'm jumping in.
No, it's the right question. And the argument, the answer to your question is in your experiment, Fleisch and Kahn's experiment. I'm of the opinion that it's the deuterium that's doing the fractionating. So I don't know that you have to add anything. And I think it's good that it's the deuterium that's doing the fractionating for you because it's what makes your experiment clean. If you put in other things to do the fractionation, like if it were in the metal ends up occasionally having disintegration pathways. So you make new elements and you destroy your host, sort of like what's seen in the Piantelli experiment, sort of what's seen in hotspots in the palladium Fleisch and Kahn's type experiment. Let me now consider the same kind of thing for carbon. So the idea is that we'd like to transfer the energy to here, but in this time, instead of breaking the energy down, we're trying to upconvert it. So the basic idea is that the strong coupling between a different strongly coupled system and the oscillator allows the energy from the oscillator to be upconverted. And once it's upconverted, it can be transferred over here to give excitation in the mercury. So that's currently the picture that I have for how the carbon experiment works. And if you like, it's the same blasted scheme. So one way to think about it is that the, well, this is what I just said, but what's important is that the pictures for Fleisch and Kahn's and picture for carbon, what's under discussion is they're the same underlying model. That this for carbon and this for Fleisch and Kahn's excess heat, basically the processes are at the heart. You're talking about the same scheme, the same model, the same process. What's going on to get you excess heat? It starts with the excited state, starts with things up here. These are going down, getting the energy over here and going into the phonons. And this is the kid's sister. The energy starts in the phonons, goes here, gets upconverted, and gets shifted over here. So one's the backwards of the other. But otherwise, they're basically the same underlying physical scheme and mechanism for upconversion to downconversion. I'm of the opinion that that's certainly an important point. Excess heat requires fractionation on the order of 10 to the 9th. It turns out Kerber's X-rays, at least by my estimates, requires inverse fractionation on the order of 10 to the 10th. So Carbu's actually working harder than the Fleisch and Kahn's experiment in order to get the X-rays out, which is interesting. It's very interesting. But on the other hand, these two numbers, they're both very big numbers and they're sort of close to one another. So in a sense, the fractionation under discussion is sort of comparable between the two experiments. Thoughts or comments or questions? Okay. I'm trying to get the points which I thought were like really interesting and important out there. Takeaway message. Well, takeaway message, in a sense, we've got these models of diffractionation. We now have versions of these models that we can connect to experiment in non-trivial ways. We have some ability to get numbers out of these models, and we have some ability to compare those numbers with experiment. That's interesting, and that's powerful. If you want to debug your theory, you need to be able to formulate theoretical problems. You need to be able to analyze and get numbers out, and you need to check the numbers and bang them against experiment to see if they got anything to do with one another. And that process for me has been ridiculously important because it's told me that my interaction was all wrong, which I've been looking at for the decade following the discovery of the lossy spin-boson. Whenever I tried to compare the predictions from these models against experiment, I was off by orders of magnitude. And that was true for every single test over a period of a decade. And that told me that my interaction was just wrong. Which leads us to the issue of the new fundamental Hamiltonian. So once I understood that the interaction was wrong, I needed to go back to the problem of what the coupling was. And I needed a direct coupling between vibrations and the internal nuclear degrees of freedom. So I want to begin making progress on the Hamiltonian. So I want to understand the new fundamental Hamiltonian better. So seemingly all we got to do is start out with the QCD Hamiltonian for the nuclei, the QED Hamiltonian for the electrons, put them together, stir them together, and Shazam them. You know, have it, right? Well, it'll turn out to be a little bit easier and simpler than that. So the place to begin. So yesterday we talked a little bit about the new relativistic model for the nuclei in a condensed matter Hamiltonian. And probably the first thing you might be asking me is, why should we need relativistic models since the nuclei are not moving very fast? And the issue is that in a relativistic description, you get a coupling between the motion, the center of mass motion, and internal nuclear degrees of freedom. And I'm interested in that coupling. And I'm interested in that coupling even when the nuclei are moving slow. So it's, if you like, it's a relativistic effect, and I wanted it to happen. You might also know that normally this coupling is rotated out with the generalized Folty-Wolthuizen transformation. And you might say, well, why doesn't it happen here? The argument is that the coupling in the spin-boson model also can be rotated out with the general Folty-Wolthuizen transformation. But if loss is present, we still get the enhancement in the energy exchange. My argument is that because relativistic models are algebraically very similar, we're going to have the same thing happen in the relativistic model. Okay, so let's think about relativity a little bit. Probably the big effect everybody uses about is that if you have a body that accelerates, it kind of like gets shorter space. Well, it contracts. So it turns out that there are other more subtle effects that are much bigger and more important. There's a coupling between the different spin states in both the electron problem and equivalently in the quark problem as well. So pictorially thinking about this, but microscopically in my mind's eye, I see more stuff going on than just this. So if you've got a nucleus that's moving back and forth, the internal guts of the nucleus is changing if you use an unrotated reference frame. And so as a result, if it's changing and you want to describe that quantum mechanically, you need to describe it in terms of a mixing between excited states. And it's as simple as that. A moving object is going to undergo internal modifications to move. And that's how our current theories are put together. And this is a small part of it. This is easy to visualize, where it's harder to visualize the spins. Okay, so in order to deal with these effects, we have to go to a relativistic theory. We've basically got to go to QCD, QED for electrons. We know what we'd like to describe. The question is how to construct a model that works this way. And when I first thought about this, I struggled with this. This is a very painful exercise to go through because the headaches and problems were produced. I'm going to explain to you sort of an answer, which is like answer number 5 or 6. This is how I go through it, which is sort of a simpler version. Mathematically, the trick is to make a basis expansion. In quantum mechanics, basis expansions are really useful and helpful. And the basis that's relevant these days is the rest frame basis states. So I want to take my description of my nucleus, and I want to describe it building up from these rest frame basis states. So my rest frame basis state satisfies a rest frame QCD Hamiltonian. In quantum mechanics, you can write things like this down like all the time easily, and people do that. If you actually wanted to calculate the energies and calculate these wave functions in detail, now you're talking major research project in general. Yeah, there's an ongoing area QCD where people are burning up a very large amount of computer time doing exactly that for nucleon and diquark levels. Okay, so the next step in this is I want to go from my general QCD Hamiltonian, I want to go to a matrix. I'm going to say Hamiltonian matrix, what's the difference? Mathematically, everything's completely equivalent. The only thing is if I go to a matrix, then my QCD Hamiltonian, if I were honest, sort of describes 1, 2 quark objects, 3 quark objects, big nuclei, small nuclei, you know, all kinds of things. It's a very general Hamiltonian. But on the other hand, if I've got a nucleus in my lattice, it's got a fixed number of nucleons, and my coupling is only going to be a modest number of states. So to some degree, if I go to my matrix, I can limit with a basis, if I choose a finite basis expansion rather than infinite basis expansion, and with a finite basis expansion, I can make the matrix smaller. I can actually have some way of reducing my description to focus on the part that I don't care about. So that's what this is, and my matrix elements are basically these. So once again, people write these kinds of things down. Actually calculating them, getting numbers for them, might require like an infinite amount of work, but these are well-defined objects that I can work with, people work with in this kind of thing. Once I've done that, now I have my theory. So for each of the nuclei in my lattice, I'm going to use one of these Hamiltonian matrices that I've developed from this process. So I just stuff it in. Because my Hamiltonian matrix has everything it needs. It knows about all the excited states. It knows how the excited states couple when the thing moves. It's got all the dynamics in it. So I'm happy as a plan. And now I've got a new theory. Of course, writing it in this fashion, it's sort of obviously and explicitly correct. And I haven't actually done anything. And the condensed matter types would look at that and they scratch it and say, this is very nice. I can't do anything with this. I don't have my H's, it's not well characterized. I don't see how the momentum comes in. I can't couple the vibrations. So I actually have to take this and take it one more step. And the one more step is that in the relativistic model, the way the kinetic energy comes in has a very specific and simple form that I can take advantage of. So the simple form looks like this. The Hamiltonian matrix, if the nucleus isn't moving, it's diagonal with all the elements being the rest mass of the states. So it's particularly simple. And in fact, the rest mass of the states, if I'm dealing with the ground state nucleus and excited state nuclei, turns out I can look up the rest masses in the tables. So all of a sudden, this part of the problem is one that's starting to look less horrible and ugly and impossible. I actually could do something with this. For the other part of it, if the nucleus moves, well, it moves because there's coupling, there's there's a coupling basically through the spins between the ground state and the rest frame and other rest frame states. And you could say, well, if I take the thing and I go into the frame where things are moving, it'll be the ground state. Yes, it'll definitely be the ground state, or a version of ground state. But if I'm working with rest frame states and it moves and I describe it in terms of rest frame states, then I'm going to produce the coupling to the other bit. So it's moving back and forth and back and forth. The only way it's able to move back and forth is by having a time-varying coupling to the various excitastates. And if you have a time-varying coupling with the excitastates, then you have the possibility for some interactions and some dynamics. In fact, you start setting things up that are going to look like a spin-boson type model. And if there's loss, it will look like a lossy spin-boson type model. So basically, at this point, without doing much of anything, at this point, this is sort of just formal, and it's a finite basis expansion for the QED, QCD states in terms of the rest frame basis. So I get this, and I'm going to plug it in, and I get my fundamental Hamiltonian. So I see my fundamental Hamiltonian is sort of the most natural thing you would do if you wanted to bring in a description of the nuclear states and the interaction with the motion of the nuclei and the lattice. This is what you would do. You wouldn't do anything else. We also recognize that this would be the next step if you wanted to have fundamental Hamiltonian to describe condensed matter were better than the one you were working with. It actually included the coupling of internal nuclear degrees of freedom. This is what it would look like. It wouldn't look like anything else. It would write an equation like this. Turns out when we first derived this in one of the papers, I was writing down a formula where basically said h squared was equal to this squared plus this squared to argue that it was sort of obvious that we recovered the relativistic energy out of it. And then it turns out that I actually constructed an A matrix and an M matrix for one special case. I found out that this wasn't true. But what's true is that the eigenstates satisfy this relationship, but the operators don't satisfy the relationship. Minor technical detail that corrects me in one of the papers. Okay. Anyway, you can see what we did. All we've done is we've taken the simplest possible formulation based on QCD and imported it into our condensed Hamiltonian, and that gives us this, and this gives us a model that either the claim or the hope, depending on how optimistic one is on a given day, is that this model is going to describe all of the anomalies in science systematically. That's to be demonstrated, but at the moment, that's the thought. Let me pause and entertain questions or comments. Everyone slow wave, raise your hand. One. All right. Yeah.
When you say a lot of work, does that mean like, a week or two? Like building up a matrices, being large matrices?
I'll talk a little bit more about that, but it's occurred to me that the amount of work that's being proposed here to produce a model that could systematically do whatever, if you like, we're proposing a new condensed matter science. We've got a new fundamental Hamiltonian. As it turns out, I'm going to be talking about sort of a new way to do the nuclear physics to be able to get the matrix elements. And the amount of work sort of implied by both of these to pursue this to sort of its logical end is a very, very large amount of work. More work than I'll be able to do this coming week. More work than I'll be able to do in my lifetime. And we're talking about something that's like big on the scale of being a program from a major scientific discipline in order to work everything out and get it explored and understood. I'm not expecting to live long enough to complete this particular exercise. I take my vitamins and exercise. It's not going to be enough. Anyway, takeaway message. So nuclear laws move, relativistic model gives us the coupling we're interested in. We've now got a new fundamental Hamiltonian. I said on the first day that I mentioned that Fleischmann-Ponce experiment presents a fundamental challenge to condensed matter theory to the nuclear physics. And before the solid-state physics folks and nuclear physics folks are going to say, well, look, you don't like our nuclear physics, you don't like our condensed matter physics? Well, you come up with one. All right. Share. So it's got condensed matter physics. It turns out it's also includes a nuclear physics description internally, but we're going to need some. We're going to have to work in nuclear physics a little bit to be able to calculate these matrix elements, unless the nuclear folks want to do their QCD calculations and extract it directly from them. But I have an idea for a way where we can have something less complicated than full-blown QCD to estimate the matrix elements. So I guess the answer is that yeah, we're proposing here a new condensed matter physics and minor modification for how to do the nuclear physics. Plus, we've got the coupling between the nuclei and the solid state, which is not in either nuclear theory or condensed matter theory at this level today. Okay, to make progress on the model, we need SI for the diagonal matrix elements and for the off-diagonal matrix elements. So the diagonal matrix elements, because these are at rest frame with their positive energy states, a lot of them are known or measured or calculated from existing theory. If they're negative energy states, then you've got some headaches involved because the negative energy state spectrum is not of interest currently in nuclear physics, or probably more of interest in QCD because it's perhaps connected to some way of doing calculation. The computation of these A matrices, that's in general much more challenging. So far, there's been 2 cases where an exploratory computation was done. And the exploratory computation was done within something called the Dirac phenomenology, at least approximately. Perturbation theory based on Dirac phenomenology. Well, since nucleons are not Dirac particles, there's errors due to that, big errors due to that. So the calculations done so far aren't all that good. Here's the result that we got from the D2 to helium 4 matrix element calculations. It's a lot of work, a lot of calculations got published, but here's the answer. We got a number. So the number for the particular calculation I was thinking is probably factor 2-ish, and probably there might be, I don't know, factor 3 or something error on top of that. The matrix element estimate's going to be too small because the nucleons aren't direct particles, but at least here's a calculation. We're able to grind the calculation through and we can get a number out. There's selection rules in this. The calculation for the deuteron coupling also gave a matrix element that sort of looks similar. And it gave selection rules out. And the selection rules we got for the deuteron calculation, I think are extremely relevant for the magnetic field effects that Mitchell's and Dennis Lutz and other people have seen as well. I think if your magnetic field polarized, basically deuteron's got 3 states, and if you can get more of them into the same state, then your G goes up and you're going up a big exponential. And I kind of think that's why people see such a big effect in enhancement. If we take this and we say, let's plug it in and estimate the maximum rate for heat production, we can get an expression that sort of looks like this. And then we can plug in numbers for the expression, and from those numbers we get numbers for excess heat out, which are in the range of the experiment as was calculated and presented by CCF 17. The bigger issue is to figure out conditions under which the fractionation can occur. So in the donor-receiver model, the weak transition, if it's rate limiting, we can analyze the model and get something that looks like this. However, for it to be rate limiting, we've got to be able to fractionate the quantity. And the calculation to show that that can be done is a different calculation than this. And so it's a tough calculation. Okay, so anyway, so nuclear physics, they've got lots of ways to do things. One way is to use direct phenomenology. And as I point out, the nucleons are not direct particles. And there's another way where they work with relativistic, rotated direct type particles. And we can't use the results of this kind of formulations directly for the calculation of A matrix elements. Although in principle, if you did it that way, depending on how you did it, you can get a better starting place. So the brainstorm for the nuclear part of the problem is to replace the direct phenomenology with basically this matrix phenomenology. So the way to think about it is, imagine you're doing a QCD calculation for your nucleons. A different kind of calculation than ones people are doing these days. Imagine that you want to get the full spectrum, so you might get the positive energy sector and different negative energy sectors, and you get the diagonal matrix elements for each of them. So you get them to plug it in. So once you know that, then you have an M matrix. Now, you're going to say, well, there's an infinite number of these bases. That's true, so you pick some finite number that you can work with that gives you a pretty good answer. And then the same thing for the transition matrix. If you're doing a QCD calculation, then from the matrix elements you can get your A matrix elements straightforward. So the proposal is to build up versions of the M and the A matrices in order to do these calculations. So this approach, I think, is described in the appendix of this paper. To actually implement this to get an M and get an A, it's going to take a lot of work. Last summer, I thought, just out of curiosity, let's take the first step. Let's take the simplest three-port model that you can possibly think of and calculate by brute force the M matrix and A matrix energy. So I did that. And so I actually now have my very first nucleon model that I could think about doing calculations of this sort with. And it would be fun to go ahead and plug it in and start getting some calculations with that to see what it is. Doing so will give me sort of my very first step towards a realistic estimate for my A matrix calculations. So lots of work. Again, what's under discussion here, if it were done seriously and systematically, is a generation to is what the work within a field. And this is now turned into a big problem, a very, very big problem. I mean, I'll be able to do some tiny pieces of it here and there, but the development of systematic tools to do this in general is a major undertaking. Let me pause. Comments or thoughts?
I got a question. It's probably a dumb question. Why does the A matrix have trivial diagonal elements? And is the fact that they're all off diagonal, why do you think that's coupled to the magnetic field?
No, the A matrix has no diagonal matrix elements. And the reason it has no diagonal matrix elements is that the energy of a moving particle involves the momentum squared. There's no linear term, so it can't be a diagonal part of it. In terms of the interactions with the magnetic field, it's much more that when you calculate the coupling matrix element, the A matrix element itself, at least for the simple model that we did, there's some selection rules that came out. These selection rules could have been derived even without calculating the detailed matrix element because they're a property of initial states and final states and angular momentum and spin momentum and stuff are. So it's just that some of them have strong coupling and some have zero coupling. So if you got uniform distribution between all the states, then you get a coupling strength that's so large. But if you have a magnetic field, you can put a lot of nuclear spin states into one of them with strong coupling, then your coupling matrix element's bigger, your G is bigger, your your coupling strength is bigger, your ability to fractionate is improved, and you're going with an exponential in terms of having things work better. So I'm of the opinion that the modest change by just modifying the number of nuclei that are in a particular spin state can have a big impact on the way the donor-receiver model fractionates and the rate at which things go.
Just a comment. It seems like, to draw a crude analogy, before you, your initial journey kind of took you up to the top of Mont Blanc, say, and that got you up there, but you didn't get to the solution, but it did give you a clear view of Mount Everest and the distance.
Oh, let me try to place things more in context. In a sense, what's under discussion here is a solution. Namely, we have donor-receiver models with which we can begin calculating things and getting estimates. There are upper limits to how fast things work. We have this more sophisticated model that we're beginning to work with, but if we pursue it, we'll get more accurate estimates, so we won't be limited to only having maximum estimates. Then we need the coupling matrix elements. We need the M and the A matrix elements. So for the M matrix elements, we actually have ways to get decent numbers, good enough numbers for most of what we need. So the only thing left is the A matrix element. So in general, to get an accurate A matrix element to 1% or something for like the 1.5 kV transition in mercury 201, that's to evolve to that, it's going to take a serious amount of work if you want to calculate by first principles. On the other hand, if you had an experiment up and running, you'd have the possibility of actually being able to measure it experimentally and have a reliable number. And it turns out for the fractionation business, I'm of the opinion that transitions to negative energy states have by far the strongest coupling. So they're going to have the strongest ability to fractionate. And it turns out, and I've got a slide that talks about that, but under those conditions, as it turns out, you can make crude estimates for the A matrix elements in that case, sort of really easy, but are going to be decently accurate enough to work with. So the answer is we, in principle, now have sort of the keys to the kingdom. If it works this way, we have the ability to get okay numbers to model everything. The issue in terms of putting this together on the same footing as current solid-state physics and current nuclear physics, that's going to involve a lot of work. And you have the possibility of pursuing this kind of approach, and over a generation or two's worth of work on the part of the community, you'd be able to have it to be up in good enough shape that you could get precision definition numbers out sort of systematically for everything you wanted to work with. So what's being outlined here is a major program. However, the notion that we're not going to be able to model anything, I don't think I agree with that. I think that we're going to have, we have the ability to do some analyses and get numbers and do some modeling now. And in fact, I think my point of view is we've actually got some evidence now that the model is consistent with Carter for the fractionation part of the problem.
So effort is perhaps better spent to fit the current theory rather and point the way to the put it on the same standing as nuclear physics and use and focus on applications to experimental results.
I think the idea is just to keep thinking about it, plugging away and make progress, and do things step by step. If at some point other folks take an interest in it, then the steps will come faster and more work will get done. I mean, in the event that nobody else takes it up, then it will peter out and go away and die and be forgotten, which is actually the more probable outcome at this point. What's more issues? Yeah, an issue is that we know that transitions involving negative energy states are the strongest. The A matrix elements will be the biggest to negative energy states, sort of systematically for all nucleons. I think that these transitions are responsible for fractionation in the Harvard experiment. Also, I think in the case of the deuteron transition in negative energy states, is probably responsible for fractionation of flesh and plasma. And the reason I think that is that because the A matrix elements are so big, under those conditions, you can get the formulas to work and get the fractionation power. For other transitions with smaller A matrix elements, it's much harder to make that work. And so at this point, I'm coming to the conclusion that it's the coupling of the vibrations to the transition in negative energy states which are making it work. And let me say at the outset, I would prefer any other explanation. Trying to explain to an audience that, well, nuclei have got negative energy states, the vibrations coupled to them, and this is fluctuation business, which is doing the business. You know, immediately the vision of angels dancing on the head of a pin arises, and it's going to be a very hard sell. So sadly, the math is going in the direction I don't like it. I would prefer any other scenario. However, this looks to me at the moment like the only way that you get connection between the numbers and what happens in the experiments. On the other hand, for theory, this is sort of a good thing, because like I say, to get quick and dirty estimates for coupling the negative energy states, that we can do, and that we have done some of so far. And the results from that look very good at the moment. And I will run out of slides fairly soon. And I apologize for dragging this along. So we want to connect between theory and experiment. So at this point, we have a new proposal for new fundamental Hamiltonian. We've got these mechanisms. We know that the new modeling gives a rate for excess heat production consistent with experiment. We know that the fractionation from these models at this point is gives numbers that can be consistent with experiment. But what we'd like to do is we'd like to move in a direction where we have a controlled experiment where we set things up, we vibrate, we put in nuclei, we look, and we know what we're doing. I mean, the Cartwood experiment is incredibly important, but it's uncontrolled. And we don't have a history of the vibrations. We don't know what the frequency is. We don't have a quantification of mercury 2 or 1 on the surface. And Cartwood doesn't even believe there's any there, but it's ubiquitous. There's mercury everywhere. We recall from last time that mercury 201 is interesting because it's got the lowest excitation energy from the ground state. I discussed vibrations going into excitation, collimated X-rays coming out, the design that exercise we went through, and then recognized that as collimated radiation 1.5 keV. So what I'm going to do is now pick up and move in this direction a little bit. So there's the pinhole camera from Cartwood experiment. There's the spectrum. There's a digitization for not quite correct interpret. The wrong formula got used for the energy dispersion. So not quite correct, but here's the peak at 1.5 keV. So this is the feature that's under discussion, which I'm interpreting as potentially it's being the result of X-ray radiation due to inverse fractionation excitation of this nuclear state in mercury vibrations, probably between 100 and 250 megahertz vibrations. There's Cartwood. This is what I look like when I had hair. Those were happier days. Similar effect had been reported earlier by Gotzi. So Gotzi was doing cold fusion experiments with palladium deuteride. He ended up doing an experiment where he had X-ray film and he saw some splotches on the film. And a very detailed analysis of the splotches were done, the geometry and everything else. Gotzi's paper is incredibly interesting. But the conclusion is that Gotzi's got a coherent effect where the nuclear dipoles in the vicinity of 90 kilovolts are going, leading to beamlets that are directed with very small angular resolution. Now, if you like, the mechanism described by Gotzi is sort of exactly the same kind of mechanism I'm thinking about as the source of Cartwood's X-rays at 1.5 kilovolts. And note also, and I don't have a slide for it, that Cartwood reported the observation of X-ray splotches on the exterior of his chamber on X-ray film. We're on the inside of the shielding. And it's seeming to me that an interpretation of that is, again, collimated emission of X-rays, probably in 25 to 30 kilovolt regime, without identification which nuclear transitions are involved. The one suggested by Gotzi is extremely interesting because it involves an upper state level. It's a metastable state. So if you had a little bit of the silver in the lattice and you had a transition, a metastable state transition, up conversion would be able to get you the excited state. It's a long lifetime upper state, so you'd be able to get the upper state and establish phase contacts, which would give you the directionality. So I think this problem is incredibly closely connected to Cartwood's collimating X-rays, and also preceded it. So the effect should be known as the Gotzi effect rather than. I refer to Cartwood's X-rays for 1.5 keV stuff specifically, but Gotzi's observations the first of this kind of thing in general. Okay. So thinking about Cartwood's X-rays, I want to draw attention to Kornilov and Vysotsky's work. We had the Yankel Massow experiment here for a while. We were testing it. We were hoping to produce an excess heat. It didn't for us. Basically, you have oil flowing through a nozzle. There's a nozzle here. As it goes through the nozzle, comes out this cavitation. Here's what it looks like. Kornilov and Vysotsky brought an X-ray detector up next to this hard plastic, and they saw some X-rays, which in other experiments they argue is collimated. After doing some experiments, SRI with a very similar X-ray detector, being much more familiar with the spectrum, I'm of the opinion that this spectrum, these aren't X-rays, sadly. I think Kornilov and Vysotsky's experiment, ridiculously important experiment. I'm one of the biggest fans. Sadly, I think this is a misinterpretation. And the reason is that their detector has a thin beryllium foil in front of it, which should absorb all X-rays below a kilovolt. And this spectrum is not noticing the beryllium window, and it should. So I think that the detector is sensing something else. I'm not sure what. Charge is one possibility, ultrasound is another possibility, noise is another possibility. But it wasn't this that I wanted to show you to impress you with. But this is something they're interested in. We've seen sort of the same effect. What I'm interested in is the water jet experiment. So they've got a jet of water coming out at high pressure. And the water jets here have a piece of steel next to it. And they have X-ray film after it. Now, the X-ray film is not going to be sensitive to the ultrasound or to charge in the same way. It's also on the other side of the steel. And they're getting basically the same pattern of exposure in two pieces of film, one after another, which is sort of an indirect proof of collimation of the X-rays. So the idea here is that the water jet is producing this very intense chaotic source of vibrations, high frequency acoustical vibrations, which are hitting the steel. The steel is vibrating, and look at the steel is being filtered. But it's a very strong, very high amplitude excitation. The lowest compressional mode in the steel is around 1 megahertz or so. I'm thinking that the steel is vibrating very strongly, transferring excitation to nuclei on the surface. In this case, I don't know if you remember my list, but number 7 on the list was an iron 57 transition, 14 keV, the famous MOSFET transition. It's possible that transition is getting excitation, producing X-rays, which are coming out collimated, which make this experiment the kid sister of Cartwood's collimated X-rays. More interesting are these experiments. You work with a bent piece of metal, and if you like, in a bent piece of metal, you can imagine the acoustical field now, and the boundary conditions flat along here. So vibrations are going to have a phase front that's going to correspond to expanding the beam. What they see is X-ray splotches which are expanded. So if you like, the defocusing of the acoustical field, in this case, is leading to a defocusing of the X-ray emission. If you go the other way, it's not defocused. And I contend that this is astonishing if people understood this experiment that they would very fast. I think this is a ridiculously important result, and one that absolutely needs to be understood better. I think that this gives you very strong evidence of conversion between acoustical radiation and X-ray energy, which would be the up-conversion effect in the discussion. Message. I'm going to have to. I'm going to flip through you guys. I'm going way over, and Mitchell's going to strangle me at some point. But we did modeling from the new Hamiltonian for the cardboard experiment. It's in this reference. But the bottom line is that we got a measure of success that brute force calculation is dotting the I's, crossing the T's, going through it like a demon. And I found a new regime that I'd overlooked before. And in this new regime, we can get the numbers to work. And from my point of view, that's a really, really big deal. Okay, takeaway message. I was arguing before that this now is a strong demonstration that theory connects with experiment, because when first done, it looked like we were getting agreement at 20% on or so. I'm of the opinion that there's an error in that calculation. The theory is saying that it fits within a window, but the edge of the window isn't so close to the experiment. So I've got to go back over that and check that. The last topic is this vibrating copper foil experiment. So the idea is that Cartwright's experiment, Visosky's experiment, this vibration and X-ray emission business, I think, well, I've argued that this is the same mechanism as how Fleisch and Pons works, which draws our attention to this as being a very, very important experiment. Cartwright's experiment, incredibly important experiment, but uncontrolled. We need a controlled version of Cartwright. So the idea was, can we take a foil, can we vibrate it on purpose at a frequency of our choosing, amplitude of our choosing? Can we put mercury on the surface? Can we transfer the energy? Can we demonstrate it, prove that that's what we're doing, prove that there's no other explanation, and clarify it? So the idea is, so here's mercury 201, the excited level. Scott states that half-life is 81 nanoseconds, which is fast. It decays by internal conversion, which means electron ejection. There's a radiated decay that's slow. So if you succeed, the first thing you expect to come out is actually electrons, not X-rays. So the idea is that basically, can we do it? Can we vibrate a foil and get some X-rays or some charges? So at SRI, some experiments were done. Fran Tanzel did it in their laboratory. So this is basically a copper foil and a resonator that's much bigger than is indicated in this diagram. There's another copper plate, a driver, a big thick driver here. And the idea is to put a voltage difference across this and have it be modulated. So the idea is when there's a voltage between here, the plate's attracted to the driver. When there's no field, it's not. And when the field changes sign, it's attracted again, and so forth. So it vibrates in back and forth. But the only thing is that we drove it at 100 kilohertz. We could get the drumhead mode excited. But I'm of the opinion the drumhead mode is too low frequency, so it's not a good match to the Cartwright experiment. Cartwright's got drumhead mode also, but the numbers work better if you're high frequency. So if you drive at higher frequency, then you push the front surface, which drives a wave to the back and hits the back and then reflects. And you can set up a standing wave. And the lowest standing wave for the compressional case is where the front moves this way and the back moves this way and then at the same time. So you're squashing, releasing, squashing, and releasing the plate. So that's what we were trying to do here. We were trying to drive a high frequency compressional mode. This is what it looks like. Resonator, foils inside here, driver made out of copper. You can bring this thing up close. It sort of looks like up close. We can put electrometer here. We can put mercury on the surface. Mercury is put on the surface. Electrometer is put out there to collect charge. And amazingly, astonishingly, we got a signal. So here's some charge emission. This is this one is L1. This is the compression that I was talking about. This guy that's really big is T2. It's the second order transverse mode. And this is sort of close to T3. So we get a big response. This is actually quite a bit of charge from a 1 centimeter size foil. The frequencies for the compression modes, L1 is at 17.2 megahertz drive frequency. Transverse modes, T2 is at 15.5, so 15.5, 17.2. That's close enough. Mainly we're sort of within the percent level of the expected frequencies of the resonances of the foil. If we go to higher drive voltage, the mechanical energy goes like the fourth power of the applied voltage. So 2 volts, 3 volts, 4 volts, that's actually a big change of the vibrational energy. And we're getting a broadening, gigantic increase in the amount of charge reported by the electrometer. If we crank up the voltage, we get sort of parabolic, quadratic increase, and then it goes into this super linear, this fast increase region, different colors here, different settings of the electrometer. And basically, at this point, we're getting so much charge, we're getting charge buildup on the electrometer, we're just keeping charge from going, which is sort of the picture. Alternatively, we've got noises filling the electrometer. It would be nice to get a confirmation that the charge is real. As of today, I still don't have a confirmation, in-event confirmation that this charge is real. So we see a strong negative current, which is consistent with the picture where electrons are coming off the surface of the metal. Here's what happens if we bias it. Before I actually thought that this is more significant than it is. The red and the green are plus and minus 5 volts bias. We're getting a spectrum that's basically the same independent of bias. If we put a bigger bias, we'll change the spectrum. So that's consistent with there being no charge present. Turns out this effect, this electron emission, is independent of mercury. The mercury on it, we get less charge than without the mercury. So the charge emission effect, if it's a real effect, is probably connected with the promotion of conduction electrons in the copper to the surface going on to O2 to make O2 minus. It's going to wander to the charge collector. That's most likely what's, at the moment, that's the conjectures, the explanation of this. We did an experiment to look for X-rays with working on the surface. We used X123 Amtech X-ray spectrometer, which is the same spectrometer used by Cornell and Visosky. This one also has a Brillouin window on the front. This is what the spectrum looks like for calibration. Here was a spectrum with a weak drive. And we had a strong drive with a signal sort of near 1.5 kV, which got all excited and I was backflips and so forth. Starting to prepare for giving a presentation on this last spring. Got worried about the calibration. Called the friend and said, we need more calibration runs. They did it, we calibrated everything. These lines went to lower in energy. They didn't respect the Brillouin foil window absorption. They're not X-rays. Sadly, I would love them to be X-rays, not X-rays. Their signal, one conjecture is the X-ray detectors responding to charge. These cannot be X-rays at the energy registered by the detector. Could be charge, could also, another lesser possibility, but also possible is ultrasound generated from the surface of the foils interfering with the detector in some way, or electrical noise of one sort. And we're going to need more experimentation to clarify that. Anyway, summary and conclusion, to get controlled curve is sort of a holy grail from my point of view. If we can vibrate a metal, see X-rays coming out, do it on purpose, uncontrolled, and be able to tear it apart and understand what's going on in detail. That would be my IT for it. I would love to see if that's true, if it's real, if we have the mechanism right. And if we had it, we can compare against models and we could figure out what's going on. I also think that Visosky and Cornell and Visosky experiment is is an incredibly important experiment, just absolutely easy to follow down. Anyway, I have a few graphs. Any final comments or questions or thoughts? You've done good by surviving this long. No.
When's the test?
Oh, that's right. I have exams for you. It's a 3-hour exam. I'm going to be graded.
Another call.
All right, so take a bio break and we'll reconvene in 5 minutes or whatever.
Yes.
Does that make any sense?
I'm gonna mute the mic.
Conventional physics will think of perturbative experiments. Okay. Yeah, and since it's a one-off, it's easy to dismiss. If you could get a control thing and actually
But the
control
thing
it.
is, as we've seen, there's Trotsky, there's Fourier, Carter, there's Hierarchy, there's Carver, there's Perturbative, and Bosonsky. And yeah, no, it's not a one-off anymore.
Okay,
It's
that's important.
very important.
Anyways, guys, we're here in the last day of Cold Fusion 101 IAP course here at MIT. I'm here with, of course, Dr. Bob. He's covering the event live for Dr. Bob's blog. The mascot for Cold Fusion, our little dog here. Anyways, pretty interesting course here so far. We actually got some our story published here in Current Science, so maybe some mainstream scientists will start paying attention to what's going on. We got a whole list of bullet points of things that are discussed in the course, and all the key points. Very good job of nailing down those key points of all the things that are discussed in the course. And of course, great. I think this is in part due to these broadcasts and bringing the attention to the worldwide audience that this is going on and has been going on for 3 consecutive years now, very successfully. And the presentations this year were definitely a lot more new stuff, a lot more thinking has been going on to a lot of these problems and stuff. I'm really excited about a lot of the progress and a lot of the developments that I've seen so far. Still want to see some experiments and get some videos of those. But anyways, we should be returning back from the lunch break shortly. Tell your friends.
Fusion. And okay, here we are on day 4. On the first day, we talked about electrochemistry and the materials and the importance of doing controls in the experiments. Second day, we talked about aqueous cold fusion systems and the importance of controlling flux to get them to be successful. And the third day, we began talking about nanomaterials and how we can make a dry, preloaded cold fusion material that we can activate with an applied electric field intensity. And I also actually went a little out of order. We showed you the optical and ionizing property emissions. So today we're going to talk about nickel cold fusion systems and magnetic systems. I'll just do a quick review. We seek for 25 years now cold fusion because of the abundance of deuterium, because of the safety, because there's pollution-free benefits, and the incredibly large energy density that we get. Hold on a moment, I'm going to change the battery in this. Okay, so the advantages are with cold fusion compared to conventional energy storage and energy production systems that we presently know. We are way outside the boundaries with respect to energy density and power density. And we seek palladium because of the high loading capacity in the absence of cracks, which tend to lose the material on the inside. We briefly talked about the importance of what the applied electric field intensity does. There is motion of the carriers, orientation, polarization, and these create dissipation. So the permittivity is actually complex. The real part is the storage, and the imaginary part is dissipation. And the reason that we talk about water is in the aqueous systems, the key to getting the loading is to get the deuterons from the solution into the metal. And what we do is we have a series of intramolecular deuteron shifts, and these end up diffusing down towards the cathode. This causes a ferroelectric orientation in the water and eventually a loading at the surface. Talk briefly about how we measure the excess heat, and we do that on the basis of showing verifiable excess heat by using multiple ways of looking for a rise in temperature, a rise in heat flow, and we make certain that our calorimetry is good by these checks. We make sure that we have no false positives by doing time integration and noise measurements. And as the data I'll show you today is similar, we always put an ohmic control next to the nano or the fusor so that we can calibrate and know what we have. Importantly, we use controls in everything we do. We do thermal ohmic controls, which are resistors. We'll use dual ohmic controls where we have a complete second calorimeter. And we often do metallic controls that do not show a cold fusion effect, where we can prove that our system is then calibrated. And so here was a check of the calorimeter where we put in a square wave. We want to get it out. We make sure we do a noise measurement so we don't get inadvertent calculations and false positives. And if we do it right, voila, we can get excess heat. So for example, here we have a heavy water fusor, which is a spiral cold work round cathode. And this is opposite an ohmic control. In this system, the power supply either sends electrical energy to the control or to the cold fusion device. Here's the controls. We see the input between 0 and 8 watts, and our delta T is much higher in the fusor. So this is it's not our power gain, but it's proportional to the power gain. And we can determine the power gain through calorimetry here. We have the power went into the control here and here and here. It went into the cold fusion system here and here and here. And we can see that although the controls, we get energy balance, we get clear excess power coming out from the fusor aqueous system. And then in the end, when we do time integration, and here is our energy in joules, this is our input energy, this is the energy gain, and over here is our power gain, the ratio of this to that. And I showed you a series of nickel systems with ordinary water that also give successful cold fusion results reproducibly. Here, for example, we have a nickel fusor with ordinary water and gold as the anode. So the ohmic control, we get a match. We measure our noise here. Here we put the input power, the electrical input to the cold fusion system, and we get more out than we put in. And we see a superlinear rise of the energy. So here is our energy gain, and this will be our power gain. I finally showed you that in our best systems, we don't have to alternate between the ohmic control and the cold fusion device. We have identical calorimeters, so we can run them at the same time, like here. Here we see the input power to the control, the measured output power. This is the integral, the energy in and out, which match. And at the same time, in an identical calorimeter, we're putting the electrical power into a fusor. Here it's heavy water, and platinum is the anode. And here's what we put in for power. Here's the power we get out. Here's our power gain. And if we integrate it, we see that we get an energy gain as well, here on the order of 20,000 joules. And we see that the excess heat continues after we apply the electric field intensity, and this was called heat after death. And we call that tardive thermal power, tardive because it comes metachronously after the application of the electric field, and the time interval of that is what Fleischmann and Pons called heat after death. We talked about the importance of the flux equations, that if you look at the flow, for example, of deuterons, there is a diffusive component. This is movement down the concentration gradient. We use for the diffusivity B because we can't use D, we're using deuterons. And here's the electrical component, so here's our electrical field minus d phi dz. And so the total amount of current flux that we get there depends on the electrophoretic mobility and the concentration. And we found out that if we take these, we can analyze the flow of deuterons through the solution as the electric field intensity is applied. It can either go up in a gas, as Professor Hagelstein described as a Tafel reaction. It can enter the metal. It can move through the metal, generating phonons, which, as you saw yesterday, is one of the sine qua nons of getting cold fusion to work. We also showed that if we divided by the concentration, we get the first order rate constants, which teach us a lot about cold fusion and why people have missed it. It says here that the rate at which deuterons enter the metal is proportional to the electrophoretic mobility times the applied electric field minus what goes up in the gas and minus what goes to fusion. We know that because E equals mc squared, if we make a joule of excess heat, we're only destroying between 10 to the 11th and 10 to the 12th deuterons that are then going on to make helium-4. So this is on the order of 0. And the important issue here is what cold fusion is not fusion by electrolysis, but 1 minus electrolysis. And for multiple reasons, when you get the gases coming up, when you're not getting loading, you're not getting the flux, and some other things also end up hurting your success of the reaction. We can take this equation, which is most important to aqueous cold fusion, and if we substitute the Einstein relation, we get this term. And we see that the entry rate of deuterons into the palladium is the ratio of two energies, the ordering energy of the applied voltage and the disorder of KT. And again, minus the amount that goes up in the gas. Finally, we saw that if we take the successful equation that describes cold fusion and we now add a second equation for the palladium itself, we can create a thing called co-deposition, whereby the result of applying an electric field, we deposit not only the deuterons, but in addition, palladium cations. And as a result, the loading in conventional cold fusion systems is very slow, whereas with co-depositional systems, we can generate the high loading ratio under an hour, get the excess heat under an hour, and we also generate vacancies that appear to be very important to how cold fusion works. Another thing that comes out of these equations are these optimal operating point manifolds. So here, for example, we are looking at the input electrical power from 0 to 8 watts. Here is our excess power. We see no excess power for any of the controls, 3 of them here. On the other hand, when the cold fusion fusor in heavy water is driven correctly so that you minimize bubble evolution, you're up here at the peak, we get our maximum output here, we're getting a excess power of 4 watts, just about 4 watts for an input of 4 watts. And as I showed you, we presented an open house of this at MIT for 5 days, and we were able to demonstrate an optimal operating point manifold there as well. The other thing is these optimal operating point manifolds seem to describe everything we see in cold fusion, from tritium production to heat production in nickel, to heat production in palladium. This is Mel-Miles values, to helium production, again from Mel-Miles. And the interesting thing is Many people claim that cold fusion is not reproducible. It is chaotic. In fact, when you plot the results as a function of power, they line up. And what's very interesting is what was initially felt to be chaotic and non-reproducible becomes very clear. So what we see is in conventional cold fusion, the excess heat is linked to helium production. We see this is the actual form factor of this we did hundreds of experiments to get this. We believe that the left side is loading limited and the right side is excessive taffel. Again, let's move on a little further. We talked about if we take these equations even beyond their metamaterials, we think that the reason that the fusors do so much better than conventional cold fusion, here we're looking down on an anode and cathode, is that we get electrical fields through the metal itself. And the result of that is by having an internal movement of deuterons, we may be creating optical phonons, which end up making this a allowable reaction, as Professor Hagelstein just showed you. Let's come back to one more thing. Let's look at the system where we have identical calorimeters and look more closely at this heat after death, where it turns out that in all of the systems we see this. Here's another one where we are driving palladium in heavy water, and we got an open circuit voltage after the reaction of 2 volts. That's consistent with excess energy. Here's our noise measurement. The blue line hides a green line behind it of the energy in, but this is the ohmic control calorimeter. And so we get a nice match here. The yellow is the input energy to the fusor. The red is the output energy from the fusor as heat. These are the powers. But looking at the energies now, as this comes back to the noise level, over here is our heat after death. And here I showed you that back in 2004, we began using heat after death for other reactions. It's another way to increase the efficacy of your cold fusion system. Not only can you improve the materials, improve the drive to get a higher power gain, but if you actually exploit it, you get another factor as well. Finally, we pointed out that Spin-boson had shown that cathodes have hot areas on them, but they did not show that these were excess heat at the time. We went through and showed they were excess heat, and when we were at the top of the optimal operating point manifold, we see a brisk near infrared output that's not there when we have a other material being heated up even at a higher temperature, which is as we see here. Here we see the input to the fusor. We see that the near infrared is increasing, and even at a higher temperature going to the ohmic control, we don't see that output. We also showed you that we were able to generate propulsion systems. For example, here are these paired Stirling engines where these are driven in electrical series, and for less power across the cold fusion system, we get rotation. And this is characterized by optimal operating point manifolds. And as I showed you, we engineer it that we drive it at the peak. And these were our results of those propulsion experiments. Finally, we talked a little bit about where we're going for generating electricity directly and eventually hitting the grand slam home run of getting a self-contained electricity generating system with net output. And we're not quite there yet. We talked about the problem we're having, mainly using fuel cells, which are high loss systems. And we learned where our other losses were in stages of raising the voltage and in switches and wires. And we're getting better at removing it. Finally, yesterday, we began talking about nanomaterials. The advantage of the nanomaterials is not only that they're dry and hermetically sealed and therefore safer than having them out, but also they're preloaded. So we talked about zirconium oxide materials with palladium and nickel, and we talked about the fact that when we drive these devices, which are 2-terminal devices, this is a 4-terminal device because we're measuring the resistance, which here was on the order of 3.5 to 4.6 megohm centimeters. And what we talked about was the problem with the nanomaterials is they are very high impedance, high resistance, but they suddenly lose that resistivity after a certain voltage, as you can see here. At approximately 23 volts, we get a drop from about 3 megohms down to here. It actually went lower. And also what happens is if you're doing an experiment and get a sudden drop off in the resistance, you're going to get a high increase in dissipation. So if you have an ammeter, it may not be protected and you may lose that as well. We pointed out that even there are therefore 3 regions of nanomaterials in terms of driving them. There is the pre-avalanche region, there's the avalanche region, the post-avalanche region, and this is where the excess heat is, as we discovered. And we showed you that in our series 3 nanors, we began getting a little bit of excess energy. Here's the ohmic control. Here is the nanor. And it's not a lot of energy excess, but a little. And it was nice to see at the beginning. And over time, we began improving it. And we learned that we lose the excess energy post-avalanche. So here's our input to the nanor. And in fact, we're getting less out than we put in. Here's our input. Here's our output. It is really important to not only know your material, but to know how to drive it. And so once we learned how to drive it, we produced series of 5 nanors, which are increased loading, hyperloaded, and advanced materials. Here was our input to the ohmic control, and the output and temperature divided by input power. That makes it a straight line. Here's our input to the nanor, and here was our output. And this ratio gives us our power gain. And we pointed out that we took these to the course in 2012, and we were getting energy gains of about 14 to 20. Here, for example, was during that course, the actual results that we got on January 30th in front of the class. Here's the input to the control. Here's the input to the nanor. And we get a higher temperature out from the nanor. And when we take the ratio of the delta T and divide by the input power, this becomes a straight line. And this ratio of this to this is our power gain. And we see that by calorimetry, input, output, a match on power, input here, and much more output power. And when we integrate it to get the energy, here is our energy gain compared to this energy input. And finally, we found that even after the course, we drove it for several more months. We showed that we had a reproducible system, but that the power gain tended to fall off slowly over time. We talked about imaging, and the important point is, here we are in our development of cold fusion. We have reproducible heat production at fairly high power gain. We're beginning to make electricity production, and our ultimate goal is to get into break-even down there. Questions before we go to the next segment? Yeah.
Do you feel you need to get to direct conversion in order to develop electrical systems? What about just doing steam?
Well, that requires a very high temperature. That would be nice to do.
Yeah, high quality steam.
We have looked at direct conversion. I showed you some of the results that did not work well. And some things we do work well, like thermoelectrics, and we hope sometime to try some of the other energy conversion devices that Peter and other people have worked on. Okay, I'm going to talk about 2 things today. One is nickel, and the other is the impact of applying magnetic field intensities to these devices. And what I'd like to just show you is, it's often believed that nickel is working with protium, and it might be. But what I'm going to show you here is we're also getting excess heat with nickel with deuterium. And we're going to show you those results in both the aqueous system and in the nanomaterial system. So here's nickel with ordinary water. It says H2O. This is not, we don't have light water. We have conductivity water, 18 megohm centimeter water when it comes out of the tap. And within a day, it drops down to about 1 megohm centimeter as the CO2 comes out of the air and equilibrates. So this is ordinary water, and gold is used as the anode. Here's our noise measurement. Here's the result of the ohmic control. The blue is the input. And we're getting more out from the cathode, the cold fusion cathode, and we see the superlinear rise, which we always see when we're getting the excess heat. This is with nickel, ordinary water, and platinum as the anode. And again, we do a noise measurement to rule out the false positives. Here's our ohmic control. We have the ohmic control 3 times. We pulse it. Each time we get back a little less than we're putting in. So here, even though we're getting excess power gain out, it's probably a little higher. This is a lower limit because we did not recover all the power here. And here's our energy. Superlinear rises where we have the excess energy coming off the nickel. Now, it was off the nickels that we first started seeing these optimal operating points. Here's what we saw for 0 to 10 watts input. And we realized when we first did it, we saw just a spot or two up here, but eventually we tried to get the whole curve. And for a number of these we did, and we began learning that these optimal operating points are really important and applicable to all systems of cold fusion, as I showed you. Back for ICCF9, I was very interested, since I had not seen any papers, of the impact of adding heavy water to ordinary water, so we figured we had to do that. And I'll show you those results now. This was the paper that was presented at ICCF9 on the impact of heavy water on the nickel light water system. So here we have, here's our noise measurement, time is over here, power on the left, energy on the right. And what we see is when we add 3.7% heavy water to our ordinary water, this was the result. Here we do an ohmic control. We add a little bit more heavy water coming up to 7.5%. So if we plot it out, here's ordinary water, here are the 2 additions. We find out that as we increase the heavy water, we're increasing the excess energy output. So years ago, I had postulated in a paper, I think back in '94, that maybe in ordinary water with nickel, we're making deuterium, but here we're adding deuterium and we're increasing the excess energy. So it appears that it's much more complicated for nickel. And in fact, it's even more complicated than we think, because if we add heavy water to nickel, we damage the fusors. Here's a virgin one that was never run. Here is one that was run in ordinary water doped with 7.5% heavy water, and it changed. It changes in color, as you can see. It darkens as opposed to looking shiny like nickel. And in the absence of the heavy water, they remain looking shiny without change. And also the resistivity changes here from 8.8 microohm centimeter down to 8. When they're overdriven, we never ever saw excess energy again. Now let's take a look over here. Here we're looking at the power gain. So this system had, with ordinary water compared to the control, we were only about 30 to 70% excess heat. And as we add T2O, we get more out. But again, once it's added, we destroy the nickel. So for example, here's our optimal operating point when we first turn it on with 14% T2O. But after running it for a long time, we actually drop this manifold down to here, and we never can go above 100% again. And this may be the strong interactions that Peter was talking about in the last experiment. We've used nickel ordinary water with the propulsion experiments. These are inside the boxes where we have these paired Stirling engines. What we end up having is a result where the light water gave us excess heat, just like the heavy water. Here with nickel, here with palladium. We also use the nickel ordinary water with the car experiments when we were trying to determine whether we could do the loop around to make net electricity. And In terms of the nanors, I showed you the nanor 77, which is a nickel nanomaterial to which we add deuterium, not protium. And here, for example, is the input to the ohmic control. Here's the input to the nanor. Here's the delta T for both. If we take the delta T and divide by input power, we get this, and these are our ratios, are our power gain. So we're seeing power gain, and here's the calorimetry. Here we get a match. Here's the energy, also close to a match. Here with the electric power source delivering the electric energy to the nanomaterial, we're getting more out. And this ratio is our power gain here. Here's our energy gain there. And we saw this over and over. We showed you yesterday that we were very interested. We had chased for 2 years to try and show the reaction continuously on both sides of the avalanche. We finally did here. On this run, we're driving this nanor, Ni with D at just over 1,000 volts. Here's our ohmic control. Here is the input power to the nanor before the avalanche. After the avalanche, it goes up as I showed you once you have the avalanche. And these are our delta T's. So what we do is we take the delta T and divide by the input power, and we get this for the ohmic control. We get this for the nanor, and we can see we're getting excess power gain here up into the avalanche, and then they match. It becomes closer to being an ohmic resistor. And although there's a slight difference here, we see the same thing with the heat flow. What initially is clearly showing excess heat coming out in terms of extra heat flow compared to the ohmic control disappears. And here we see it with the calorimetry, where this is our power gain is these ratios, and here it goes below what we expect. So here is our power gain as a function of time, ohmic control, brisk excess energy, avalanche, and it comes back to equivalent almost to an ohmic resistor. Questions? Yeah.
So, did you ever go through the exercise of working with a palladium fuse or running it with light water and adding a little bit of D2O?
No, that's what we need to do. That's what we really need to do is get isotopically pure H2O.
Well, I was thinking,
Hopefully this year.
well, I was thinking you talked a little bit about nickel. I'm just wondering what the story is with palladium and that kind of study.
I just hadn't done it yet. For the most part, we just hadn't done it. If this was a better funded field, we would have answers to that important, so important question. Let's look at the application of magnetic fields. How does a nanor respond to applied magnetic fields? Now, magnetic fields and applied radio frequency and electromagnetic effects have been described before, initially by Dennis Cravens, by Bachris, by Stan Spaw. We had a paper come out more recently. And a series of things have shown that when the magnetic field is perpendicular near the cathode, often we can switch off the effects. And Dennis Letts reports it here. And we saw in fact that when we take the fusor and apply a perpendicular magnetic field intensity to the electric field, which is going through, we can actually increase the solution resistance. When we plug in the equations, it indicates that that would improve loading. So one of the things that we're seeing is magnetic fields may have multiple effects. I'm going to show you where they increase the energy gain, but under some conditions, they may do something else. For example, here we were looking for direct electricity conversion using ultrasound. And what we do is we have an ultrasonic horn, we have a series of nanors, and the important point here is that when we use ultrasonics and a magnetic field, we're getting less output. So here's the ultrasound magnetic field. We're doing magnetic controls to make sure we're not missing anything, as well as the ohmic control. So we're getting results in this case where what we think we're doing is changing the conductivity in this equation. This has to do with what goes up in the gas, and we think that that's where it affects there. We've also examined, when we had the nanor at MIT, what's the impact of first static magnetic fields and then an AC magnetic field, and we'll talk about that now. Now, this was the nanor, the Series 6 nanor that we brought to MIT in 2012 to this course. And it has about 50 milligrams of material in it. And so let's look at the impact of magnetic field. So here's no applied magnetic field. Time is in this direction. We're looking at the power into the ohmic controls here. We're looking at the power into the nanors here. And what we're looking at is the delta T normalized to input power, which is in red. So the ratios, again, are here to here. So that's no field. Here's the calorimetry with no field. Also, remember, look how this is coming down. Here we're looking at the delta T with no field, no field. We saw these yesterday, but we want to show them for comparison. Okay, so now we take our device and we're going to put on a series of 3 DC magnets where we're going to have increasing magnetic field intensity. Here's the first one. Then we increase the field. I'll show you the results of the differences in a moment. This is with the heat flow normalized to input power. Then we increase the field with a larger magnet. Here's our ohmic control, ohmic control, ohmic control. This is nanor. So our this is calorimetry. So it's this to here is our ratio, our power gain. And here's the delta T to input power, heat flow to input power. So what did it show? Hold on here. We did one other one with the 7-8 nanor. I'll better come back to that in a bit. What we saw is the greatest impact here. We're getting increases in energy gain. It's mainly a current source. We're having a Norton equivalent driving it, so it's not much there. And here's our results. If we look, this is no applied magnetic field, a small magnet, a larger magnet, and the largest lab magnet we could find. So the increasing magnetic field is in this direction. Here's our energy gain. And here's the incremental magnetic field effect for DC. Magnetic field. It's up to a factor of about 3 or 4. So what we find is the DC magnetic fields do have a small effect, but it might be inhibitory, especially when it's perpendicular to the magnetic field. However, at higher currents, we see a small to moderate increased gain. Now let's look at the AC. We took some of these devices and wanted to use a very large magnetic field. So what we did, we had 1.5 Tesla. We flipped it once a second, but in a 10th millisecond time. This produces on the order of 40,000 volts per meter at 5 centimeters. And we were at a distance of approximately 20 to 30 centimeters away and moved it closer, as you'll see, over a series of times. We also have a longer run than we did at MIT because we wanted to make sure that we would be able to see changes that might take longer. So we ran 2 nanors, 6.1 and 633. 633 we also used with CR39, as I showed you yesterday. Now what happens is we induce the magnetic field using a coil, and what happens is under the right-hand rule, we end up having the current going this way. We make a magnetic field here, as you can see in this cartoon. And so what we do is we're driving the nanor. Here is the nanor, the ohmic control, one of the temperature sensors between them. There's other temperature. This is just a cartoon. You only see 3 temperature sensors here, but we have more than half a dozen plus the heat flow. And we put the magnetization driving field up on top. So here's with no magnetic field. We have to do that control. And it's very similar to what we saw at MIT. So we decided now to try the magnetic field. And as I mentioned, the times of the experiment were lengthened compared to what we were doing at MIT because we weren't sure if there might be magnetization, other things involved. And here was our first run. There's a back of the envelope first run. Here's the ohmic control. Here is the nanor. Here's the ohmic control, nanor. Now we're only putting on the magnetic field between here and here. So this is not a DC field. This is an AC field. So there's approximately 3,000 to 4,000 pulses that occur between here and here. And there's no more afterwards. And what you can see is there's not much change compared to the ohmic control, but a very large change compared to not having the magnetic field intensity there. And we see similar results for the delta T here versus here with the no additional field. And here we see the calorimetry. Let's go to a higher DHDT. And again, we see it. Here we're up to 0.45 Tesla, which we're flipping every 10th millisecond. And compared to no field, we're seeing a big effect. And we're seeing it with delta T. Here's the magnetic, remember the magnetic field is only here to here. So we see it here, we don't see it over there. We see it with the heat flow, here with the calorimetry. Now this is interesting. Here's our ohmic controls. A lot of runs here, a lot of duty cycles. And here is where the magnetic field is applied. It stands out from all the others. But something else stands out. There is a long-term metachronous effect. Remember before I showed you the fall off was exponential for the peaks. We don't see that now. What we see is that it goes down, it goes up, it goes down. It's not doing what it did before, and we'll talk more about that in a bit. Let's go to a higher field. The same thing happened. Here's the heat flow. Here is the, this is interesting. This is, on June 8th, we kept running it. There's no more DHDT field here. But this is after the DHDT field. Notice how it's going up and down. And we see that this is not what we saw before. For both delta T and for the calorimetry, for the heat flow, we always saw an exponential fall off, and we don't see it here. What we see is, I'll get one of these where we see it a bit better. Here it is. There's a metachronous run. No DHDT, but it's increasing. We'll come back to the other things here. Here's another one. This is after treatment. We call these M nanors. Once they've been exposed to a very high magnetic field intensity, they don't behave like the other nanors. So we give them a new name, M for magnetic. So look here. Ohmic control nanor, ohmic control nanor. It doesn't go down exponentially anymore. It's going up. There's no magnetic field applied here. There's some kind of interaction, possibly, in the material itself, either interacting within the material or within the material in the electric field that we've never seen before. Let's go back here and talk about some other stuff. We also looked at the impact of bringing the field very close and applying an orthogonal field, and we wrecked the equipment as you see it here. We'll come back to the warning in a bit. Just as Peter gives you a warning about cold fusion on your career, if you do this experiment, it's a warning on your equipment. You may lose it. I don't mind because we found so much here. So here, when we're driving it at just under 0.3 Tesla, that we flip every 10th millisecond, we get a massive output. And notice here, it doesn't keep going down exponentially, it's going up again. Okay, and then we show the metachronous run. And I think this is a real issue we have to think about. So here's a nanor over time, exponential fall off. And here's an M nanor with no magnetic field around. And it's acting different. You're going to see it has higher gain. It has metachronous effects, and we'll talk about that now. Now, the thing that really blew me away when we did these experiments is I expected, I showed you these optimal operating plane manifolds where we're looking at the output as a function of input power. Everything we looked at, we had only seen one optimal operating point. So I thought when we would apply these DH details, this is out of my lab notebook, I thought we would increase it, maybe make it rise, or if it was perpendicular, it would go down. Instead, this is what happened. This field, I had to shrink down the manifold to get this all in the graph. This blue line is conventional cold fusion. So this one used to be up here. I had to bring the curve down. So this is what we used to think was the cat's meow. And now with the magnetic field, the DHDT field, we're finding a very big number of changes. One, the peak optimal operating point manifold increases in height. So for example, while the magnetic field is on, we rise, we go to higher amounts. The other thing that really blew me away was we get a second optimal operating point manifold. So we don't get one anymore, we get two. We were calling that on that day the MOOP because I was hypothesizing without any evidence that maybe our lossy spin boson, our loss for the spin boson technique was for magnons versus phonons. But that remains to be seen. The important point here is we hypothesized something simple, and what nature actually gave us was something much more complicated. And what it gave us was an improved optimal operating point. We were able to increase the output of these devices and rejuvenate them with the DHDT, and we could also create this new optimal operating point manifold. So what we found was, in summary, application of high-intensity fractionated magnetic fields, here up to 1.5 Tesla, where we flip it in a 10th millisecond and do a series of pulses, is that we can have a major effect on the amplification of these nanors. Two, there are synchronous and residual metachronous effects. Metachronous means after we treat them with the magnetic field. There's evidence of two optimal operating points for the first time. We see that the initial one that we saw increases in height and a new one appears while the field is on. We've never seen that before, and so these are magnetically induced, never seen before optimal operating point manifolds. In terms of what the result was, we created an increase up to 10 times peak power gain on the nanor, up to 4 times by calorimetry, and the net result was that the M nanors, the Series 6 M nanors we treated, had outputs that range from 22 to 80 times input. And that's what we presented at ICCF 18. The important points that I think we ought to think about in the long run are, what are these metachronous late appearing effects? What have we done to the material? There clearly is a new material science here. We're inducing something that wasn't there before. It gives us more power out from cold fusion. It gives us apparently new processes because there's a new optimal operating point manifold. And some of these linger, but they not only persist after the application of the field, but they have dynamic changes over time. So one hypothesis I made, I don't think Peter agrees, but one hypothesis that I used for my thinking, maybe we have a first stage allowed by phonons, and maybe we're having the second stage mediated by the magnetic effects for whatever reason. The important point is M nanors, like nanors, are a useful, dry, preloaded way to do cold fusion. They give high energy outputs and eventually can be used integrable into circuits and will allow us to maybe change electrical engineering and how we deal with things. Here's my warning label. When you use the high intensity magnetic fields, beware, you may ruin your equipment if it's too close. You've got to be very careful. But if you do, you can get a big difference in gain, just like we did with the Fusor metamaterial, just like we do for optimal operating point control, just as we do for controlling heat after death. Our future plans are to look at these magnetic domains. We're very interested in them now. We've built scanners to look at the domains, and hopefully at the next international conference we'll present the results. One thing that we do have to really think about is why are we getting these responses? Here, the metachronous effect, where the peak gain is no longer regular, no longer falling down exponentially. And hopefully you will eventually tell us why. So thanks for coming. That's going to end what I'm going to talk about today. Any questions? Yeah.
The enhanced performance for magnetic effects that you're describing here, is that, and I saw in your future plans, this is what you're going to do specifically with respect to the magnetic magnetic field investigations. Does it have an impact on your overall experimental plans as well? In other words, are you always going to apply the magnetic field like, say, MEMS does?
We don't. I mean, one of the things, no, we don't always.
Okay. So it depends, I guess, on what your objectives are in a particular set of experiments or a series of nanos.
I think you have to do the control. You've got to do the material. You've got to do the material plus the protium or the deuterium. You've got to totally investigate it. Then you've got to look at the impact of adding the magnetic field. So I have no problem with adding it, but I think you've got to look at the incremental effect. Okay. Thank you.